This lesson is an overview of the high-level concurrent types that programming languages such as Java offer in order to take the burden off the programmer when it comes to thread pooling, thread synchronization, and the like. After this overview, a series of code examples will illustrate some of the data types shown in the overview. Let me begin with something we've seen already. Java has a package, java.util.concurrent.atomic, that contains a number of types. You see the 4 listed here, and the top one we've seen already, the atomic integer. All of these types have synchronization baked into the data type so that the programmer can create instances of these things, for example, an atomic integer, and then use that instance without having to worry about thread synchronization. In other words, type safety comes with the data type. In the case of the atomic integer, I thought it might be useful to see what an implementation would look like. So here's a simplified atomic integer. I'm going to call it a counter. It doesn't have the full functionality of the atomic integer, but it has enough to give the basic idea. So I have a value initialized to 0, and then I have a pair of methods which are synchronized. So recall that that means exactly one of these can be executed at any time. So the first is called getValue, and the other is called increment. GetValue just returns the current value of the counter. Increment does a bit more. It first checks to make sure that the value hasn't overflowed. If it has, we throw an exception. Otherwise, the value is incremented and the new incremented value is returned. So under the hood, atomic integer does this sort of thing. It has synchronized methods. It makes sure that instances of the data type can be used in a thread-safe way. Before moving into the more elaborate data types, the collection types, let me introduce some jargon that will simplify matters. A read operation, as you know, has no side effects. So if I read something in an array, I don't thereby change it. Let's call that a retrieval operation, just so we have clear jargon. And an update operation does have side effects. So update operations would include writes, additions, that sort of thing, editing, deletions, whatever. So retrieval, no side effects, update, side effects. Now let me turn to the first of the really nice thread-safe types provided in java.util.concurrent. You can see here the concurrent hash map. With respect to functionality, this has the same functionality as the old hash table, but it's much more efficient. Under the hood, the concurrent hash map is partitioned so that you could have, in effect, 2 concurrent updates, so 2 concurrent changes to the concurrent hash map, so long as these occurred in different partitions. You couldn't simultaneously, of course, change the value of the same key at the same time. That would be blocked. Retrieval operations in general in the concurrent hash map don't block at all. Very nicely done. And the entire hash map instance cannot be locked. That's built into the implementation. So the concurrent hash map is nice because it is thread safe. We want that. But it's also highly efficient. It's fast. In similar fashion, the copy on write array list does for lists what the concurrent hash map does for maps. Again, the copy on write array list has essentially the same functionality as the old Java vector, which is also thread safe, but not in the same efficient way that the copy on write array list is. There are some other thread safe types that we're going to see. In fact, the first example that we'll see in code will use a queue. So we'll look at a blocking queue. And I've given a brief description here, but since we're going to do a code example, I'll wait for further examples or further details until then. Now let me turn to something else, executors and thread pools, and let me use code examples to describe. In the Java code we've seen so far, you've seen idioms like this. New thread, runnable is an object reference that points to some object that encapsulates the run method. So new thread, runnable, start. So we start a thread. Now, what's important to note is that this should be taken quite literally. In other words, new thread generates a brand new thread and then starts that brand new thread. so there's some overhead associated with this. In the new preferred idiom, we use an executor, and we'll see details of that later, but for now, let me just rely on your intuitions. We're going to create an executor, in other words, a thread executor, and we're going to call execute on runnable. And the difference is this. The difference is not just syntax. The execute method may use a thread taken from a thread pool that the executor has already built. In other words, the difference between this new thread start and execute is efficiency, and that's really important. So I summarized some details down here. We'll come back to those details when we do various code examples. One of the code examples I'm going to do is in the fork join executor service. And this is a very, very nice service that Java has provided in its new support for concurrency. And let me explain it with a simple example, and then I'll look forward to a richer example that we'll look at. Consider this tree structure. So this is basically an arithmetic expression. What it adds together is A times B and C plus D, as you can see from the tree structure. Now, if you think about this concurrently, what you could be doing concurrently is computing the product of A and B and computing the sum of C and D. And once those two subtasks were completed, you could then add them together to get the result. The fork join service is ideal for these sorts of recursive problems. In other words, problems that can be broken up into subproblems that have essentially the same structure as the original problem. The example that we're going to look at is a bit richer. We're going to do a search of the file system because a modern file system has a tree structure. Now, what's nice about the fork join executor service is that it has a thread pool under the hood we don't have to worry about, but it's also quite clever because the workers are assigned tasks automatically, and if one worker winds up with less to do than another, then the worker that is not so busy can actually steal work from the worker that is busier. So it's a very clever and efficient implementation, and we'll have a chance to look at those details a bit later. So this has been a whirlwind tour through the high-level, thread-safe structures that Java provides. Other languages provide comparable data types nowadays. So this whirlwind tour has had to skip over some details, but the details will come to the fore when we look at the coding examples. This lesson presents an overview of our first example of a high-level, thread-safe collection in Java. The working file you're looking at in the Emacs editor is BlockingQueue overview.txt. Let me get to the data types. The package java.util.concurrent has two data types of interest in this example. The first is an interface, BlockingQueue. We'll get to what the blocking means momentarily. And the second data type is one of the interface's implementations, synchronous queue. So let me get to the blocking and synchronous, which basically have the same connotation in this example. So the synchronous queue has an insert operation and a remove operation, as you'd expect. There are some other operations, but those would be the two principal ones. And the idea is that the insert operation blocks. It waits until a remove operation occurs. So if we jump a little bit ahead, I can show you what the example is going to do. I'm going to have a producer thread and a consumer thread, and in between the two is going to be a synchronous queue. The producer, in fact, there are going to be two producers. A producer puts an item into the queue and basically waits until the consumer extracts that item. So the blocking occurs on the insert that the producer does. Now, if you look at this a bit more technically, if we move back up here, a synchronous queue does not have any internal buffering. In other words, it doesn't actually save anything. It basically forwards something from a producer to a consumer. In this sense, the synchronous queue really acts as a pipe, and that's how it's going to be used in this particular example. The blocking queue does have other implementations. There are several standard implementations that ship with core Java. For example, an array blocking queue does have a buffering capacity. But in this example, we're taking perhaps the simplest implementation of the blocking queue, which again is the synchronous queue. Of particular interest to us is that the synchronous queue is thread safe. And in order to demonstrate this, you'll see when we get to the source code, I'm going to have a single consumer, but I'm going to have a pair of producers. There's not going to be any explicit synchronization because the synchronous queue implements the synchronization. Let me turn to a second topic. This is something we've seen in code examples, but we've not actually taken a step back to consider. So the Java Lang package, the core package, includes, of course, the thread class, which we've seen a couple of times. It also includes the runnable interface, and the thread class implements the runnable interface. The runnable interface is very, very simple. It declares a single method, you see it here, public void run, and the thread class provides an empty implementation. So it exhibits what's sometimes called the adapter pattern, and the implementation conceptually is what you see on this line. You have the implementation of run, open brace, close brace, so there's no operation, run returns immediately. What this means for you and me as programmers is this. We could write a class that implements the runnable interface. We could also write a class that subclasses the thread class. In either case, to do any meaningful work, we need to override run. Which way we go is really a matter sometimes of preference, other times of convenience. In the example I'm going to show you in the next lesson, I'm going to use both the runnable interface and the thread classes. Now let me make one minor point here. The runnable interface does not have a start method. Notice, there's a single method, run. So in order to start a thread, it's still necessary to call start on a thread object. Now let me define the program structure a little more clearly. I have a class that encapsulates main. It's called the producer consumer queue class, and it's going to create a synchronous queue. I'm going to call this Dropbox for obvious reasons, because producers are going to drop stuff in there and the consumer is going to take stuff out of there. There are going to be two producer threads and a single consumer thread. We could have any number of producers or consumers. The idea here is to exhibit the thread safety, to show that we don't have to do any explicit synchronization. Nonetheless, the runtime system, because of the data types involved, is going to get it right. The producer threads are going to insert strings. It's a pretty straightforward example into the queue. And the consumer thread is going to remove those strings one at a time and then print them out. In this lesson, we're going to look at the source code for the BlockingQueue example. The working file you see is producer-consumer-queue.java, and the first two lines of comment at the top show how it can be compiled and run at the command line, and we'll run it, of course, before the lesson is over. The imports show the data types of interest. So the first, BlockingQueue, is an interface type. There are various standard implementations of this interface. The one we're going to use is the synchronous queue. And just as a reminder, the synchronous queue behaves in effect like a pipe. It doesn't buffer anything that's inserted into it. Instead, when a producer inserts something into the queue, the producer blocks until the item is removed from the queue. So it has straightforward pipe behavior. Java.util.random is used to introduce random sleeps. I'm trying to get a realistic look and feel to the program. So line 1 in the source is straightforward. It creates a synchronous queue. That's the implementation that's going to hold strings. And then we're going to create basically 3 threads. So the main thread is doing the creation here. The first thread is a producer, and that thread is started. The next thread is a consumer. The second argument there, the 12, indicates the number of removals the consumer is going to do in total. Each producer is going to insert 6 strings into the Dropbox. That thread is started. And then for good measure, a second producer. The idea is to have multiple threads accessing the synchronous queue concurrently in order to establish that we get the thread-safe behavior promised by the implementation. And we do indeed get it. So Java's done a nice job here. Now, the producer and the consumer both have the same pattern. Each of these classes implements the runnable interface instead of subclassing the thread class. So I'm going to do a little bit of variety here. The producer, as you can see, has a private member called Dropbox, and the constructor simply initializes that field in the appropriate way. For us, the important method is run, the override. So the producer is going to execute the following code. I've hardwired the data into run for simplicity. So these are 6 strings, rather silly, as you can see. And in a try block, because the put operation can throw an exception, we go into a for loop and basically insert each of these strings in order into the Dropbox, into the blocking queue. So those put operations, those insert, are going to block until the consumer reads each of these in turn. The consumer is noted very similar. It also has a local field of type BlockingQueue string. Max takes is the maximum number of reads it's going to do, and in this case that's hardwired to 12, as we saw above. So the constructor just initializes those fields, and once again the method of interest is the run, because this is what the consumer is going to implement. In this case we have a counted loop. We're just depending on the fact that there are going to be 12 reads and no more than that. And so the first thing the consumer does is to remove something from the queue. Again, this is conceptual because the synchronous queue is really a pipe. It's this take operation that then allows the producer to continue its flow of control. So a message is read from the queue, printed out, and then just to get a little bit of randomness into the program, the thread sleeps for a bit and then continues to do its work. So let's go to the command line and give this a try. I've already compiled the code. I'm now going to execute it. Now what we're going to see here is that each of these strings should be printed twice because the 2 producers are producing the same data for the consumer. And there's a little bit of jerkiness here, which reflects, of course, the random sleeps that are going on. And if you eyeball this and do a quick count, you'll see that indeed there are 12 strings, and everything has worked exactly as it should. So, for example, none of the output is scrambled. Apparently, there has been no conflict. There have been no race conditions. We don't expect those because the implementation, if we go back to the editor, and jump all the way back up to those imports, it's because the implementation in java.util.concurrent synchronous queue has done the required synchronization under the hood. This lesson is an overview of a forthcoming code example. I'm going to call the code example the ski rental example. It's in Java, and it introduces 2 constructs that are high level and that provide very nice support for concurrent programming. The constructs are the semaphore and the executor service. Let me take these in turn, and let me review semaphores by using a non-technical example. Suppose we have a small movie theater. It seats 300. We're going to show a movie. We'd like to have a packed house, so we issue 300 tickets. Each of those tickets gives access to a protected resource, the movie theater. But the access, of course, is not exclusive because we can have up to 300 patrons in the movie at the same time. In this scenario, a mutex would be inappropriate, certainly from a business point of view, because a mutex would allow at most 1 patron to enter the theater, and it would exclude all others. So the mutex connotes mutual exclusion, whereas the semaphore does not. So in the semaphore example that we're going to see, we will have some exclusion, but it won't be mutual exclusion. Let me turn now to the executor service, which we've talked about a little, but we've not really seen in the flesh. I'm going to return to an earlier example, but look at it a bit more carefully. The cursor right now, By the way, the working file is Semaphore-Overview.txt. So the cursor right now is to the left of this line, new thread, the argument is runnable, and then we're calling start. So the idea here is that this line explicitly creates a new thread. That's a relatively expensive operation. The argument is a reference to an object that encapsulates the run method. That's the code that's going to be executed when the thread is started and we start the thread. So in classic Java, this is how you would do multi-threading. You would explicitly create a thread and then start that thread. Now let's look at the new approach. We have an executor service. The object reference is exec. I've not shown how that's created yet. We can wait on that. And we now call execute, and the object again is this runnable object reference. The difference is significant. The executor service is almost for sure going to use a thread already created and saved in a pool in order to do the execution of the runnable. What we have here is a higher level approach to starting the thread, and it's also, in general, a more efficient approach. Now let me turn to the ski rental application. It's got 3 classes in it. There's a little bit of complexity, so a quick overview will be useful. So the most obvious class is the ski pair. It's a very simple POJO class. It has just 2 properties, name, so that we can print information to the screen about the ski, and the Boolean property in use, which indicates whether the ski pair has been rented out or is still in the inventory. So the ski pair class is the base level class, if you like. The skis for rent class represents the inventory of ski pairs, and it's got some synchronization in there, explicit synchronization. In particular, there's a pair of synchronized methods, getSkiPair, which will return the next ski pair to be rented if there is such a pair. Everything might have already been rented. And the companion method is returnable, which again is Boolean. It indicates whether the skis have currently been rented out, are in use, and are ready to be returned. So that's a true-false property. There are some other methods, and they support the inventory bookkeeping. As a slight twist in the application logic, the application makes sure that the semaphore count is always less than the inventory count. In other words, we're always holding back some ski pairs just in case, so that we never run out. Now let me return to the synchronized methods. Even though this example uses an executor service, which is high level, uses a semaphore, which is high level, it also uses relatively low level synchronization. And that's because this is the most straightforward way to do the synchronization. In other words, even with the wonderful additions that Java has made with java.util.concurrent, there are still situations in which a synchronized block is the most straightforward and obvious way to go. And I think in this example, that happens to be the case. Finally, each ski pair is simulated as a runnable object. And you might say, as the runnable object is executing, that represents somebody using the ski pair to do the skiing. In order to keep things as robust as possible, the executor service has a thread pool that exceeds by 1 the number of skis in the inventory. So as we'll see, when you create an executor service, you have some say about it. You can suggest, basically, how big you think the thread pool ought to be, and you can specify other properties of the threads that are going to be in that pool. So this overview will put us in good position when we turn to the source code. We'll do that in the next lesson. Right now, let's take a short pause. In this lesson, we're going to look at the source code for the ski rental example, and then run the code. Let me begin with the imports. So you see the cursor in the file semaphores.java. That's the source code, is set to java.util.concurrent.executors. So executors are, in effect, threads from a thread pool, and java.util.concurrent, of course, is the package that contains the high-level thread-safe constructs that we're currently investigating. The executor service manages the executors. We'll see that at the source code level momentarily. And the semaphore is the counting semaphore that we described in the overview. So it restricts access to a resource but it is not so restrictive as a mutex. In other words, a semaphore need not have mutual exclusion as its goal. The ski pair class is straightforward. It's a POJO class with two properties: a name to identify the ski. We want to print information about it, and the in-use property, which indicates whether the ski pair is currently out being used by a skier. The skis for rent class represents the inventory, so as you can see, there are 150 ski pairs available for renting, but we want to hold some back in case a big shot shows up. So the minimum number we're going to keep in stock is going to be 5. The semaphore is then defined to be the maximum number of ski pairs minus the minimum we want to keep in stock, so basically 145 in this example. You might say that's the number of tickets. So we've got a semaphore, a counting semaphore in particular, with the count value set at 145. The array named inventory is going to be populated, as you would guess, in a constructor, and that's done right here. Now, the methods of interest are semaphore acquire and down here at line 8, semaphore release. So we acquire a semaphore and we release a semaphore. This is very close, of course, to the idea of acquiring and releasing a lock, except the semaphore is not an exclusive lock. You'll notice that neither acquire nor release is in a synchronized block, and that's because each of these is thread safe. So the thread safety is, again, baked into the semaphore data type, in particular into these methods. So if we can acquire a semaphore, and we do that right here, we return a ski pair, so we have a ticket for a particular ski pair, and then when we return, we release the semaphore. Now, even though acquire and release are not in synchronized blocks, I do have a pair of synchronized methods, and let me just review very quickly what this means. When you have two methods, in this case, that are synchronized, what you're doing in effect is locking the pair. In other words, at most, one thread can be executing either getSkiPair or is returnable. Now, the use of a synchronized block in an example such as this indicates the following. Even when you're using high-level thread management constructs, the Semaphore-Executors and so forth, there are still occasions when the low-level synchronized block is what you really need. Are there ways to avoid this in principle? Yes, you could do so, but in this particular case, this is the most straightforward approach, and so it's the approach that I've taken. So let me explain the logic here and the challenge. The reason these two are synchronized as a pair is that we cannot have a ski pair being sent out for rental and being returned at the very same instant. So we have to make sure that a ski pair that's going to go out to be rented is currently in the inventory. Also, we cannot actually bring back a ski pair into the inventory unless it's currently out, unless there's a skier using it. So to keep the logic clean, we need to synchronize these two methods. So getSkiPair, all it really does is it checks to make sure that the ski pair is currently in use, and all isReturnable does is basically the same thing. So if the ski pair is in use, we set it to not being in use. In other words, it's now in inventory. So there is some low-level synchronization required, but the synchronization is not on the semaphore methods, again, acquire and release, because those have the synchronization built in. Finally, the class Semaphores puts it all together, so let me do a quick overview of that, and then we'll do a sample run. In order to get some randomness into the simulation, I'm going to use a random number generator with a little bit of sleeping. We've seen that many times before. I create a skis for rent object, so that represents my inventory. I now need a runnable object to represent a skier, basically the process of renting the skis, skiing, and then returning the skis. So the by now familiar run method does all of that. For logging purposes, we're going to get the name of the current thread that's been given to us by the executor service, and then we're going to go into an infinite loop, so this program has to be killed at the command line. We have a skier try to get a ski pair. We print out information about that. The skier then goes skiing for a random amount of time, up to 2 seconds in this example. We log a message about returning the ski pair, and then we actually return the ski pair. So that's basically the skiing activity. For the executor service, I call this executors. We create a new executor service, and basically the size of the thread pool I want to be max ski pairs plus 1. So I'm being a little bit conservative here. I'm going to have more threads than I actually need. We could fine-tune this, of course, in a production environment by doing profiling and the like. Now, in the executor service, I'm going to iterate over these executors, and for each one of them, I'm going to create, you can see here at line 14, a single thread executor. Basically, this means I'm going to have a pool with a single thread in it. So the multiplicity is going to come in the pools. There are going to be many pools, but each pool will have only one thread. This is a very simple thread model. And then for each of these, we're going to execute. So the idea is the executor service will have a thread pool of a certain size, and as skiers are created that need to go out and do the skiing, the executor service will pick a thread from the pool to execute the skiing task. So it's nice and clean, it's high level. We don't get into the low-level details of starting threads and all of that. Now let me go to the command line and actually run this. This will give us a little bit of insight into what's happening. I've compiled the code already. I'm going to start executing and then kill it immediately at the command line. And I'm going to move the cursor down just to some arbitrary position. So we'll start, for example, here. We've got pool 38 thread 1, renting ski pair 37. So pool 38, pool 93 below it, pool 55 a bit further down. These are all of those single-threaded pools that we had the executor service create. And each thread from that pool is going to represent one skier. So a skier is going to rent a ski pair, do some skiing, and return it. If you have a really slow weekend and you study this output, what you'll see is that there are no overlaps. So there's no case, for example, when a ski pair is out already and it's also being rented to a new skier. So the synchronization is done correctly, but the synchronization is much richer than the sort you get with a mutex, because in this case, we're using a semaphore. In forthcoming examples, we'll see the executor service again, sometimes explicitly, sometimes under the hood. This lesson presents an overview of the Filesearcher program. This program uses the fork join framework, and that framework in Java provides very high-level constructs for doing concurrent programming. You're looking at the working file, Filesearcher Overview.txt, and we'll go through some of the details momentarily. First, however, I'd like to move to the command line in order to motivate the Filesearcher example. So I'm here at the command line. I'm on a laptop, a Mac machine, so a Unix-type machine, and let me list the root directory of the file system, which is just a slash. And you can see there several entries, basically 3 columns of entries, all of which are subdirectories. So slash is a directory. A directory is just a file in a Unix-type system that holds other files. So a directory can have a mix of non-directory files and subdirectories. In this case, we're looking at all subdirectories. And if I pick one of the subdirectories, etc., for example, and list that, you now get a list of subdirectories plus non-subdirectory files. The details aren't important to us right now. What is important is the idea that the file system has a tree structure. This is the same, of course, on a Windows system. The only difference is that on a Windows system, as opposed to a Unix-like system, you can have multiple roots for the file system. In a Unix system, you have a single root, and that again is the slash. Let me return then to the Emacs editor and the working file, and talk a little bit about the details of the fork join framework and how it's going to be used. I'd like to start with this point. In the fork join framework, the implementation details of the multi-threading are kept under the hood. We really don't see those at all, and the programmer is able to take a very high-level view of the problem at hand. So let me describe the problem at hand and refer down here to some of the details. The file searcher is going to search a specified tree in the file system. So it could start at a root directory, at a subdirectory at some level. I'll come back to that momentarily. It's going to search for files with a certain extension. I have this hardwired to search for files that end in .txt. So the extension is .txt. The file searcher, for example, is going to pick up all of the working files that we've been looking at. But any file extension would do, and we could easily change the program so that the file extension could be given as a command line argument. In this case, for simplicity, it's hardwired into the code. Now, in searching the file system, the file searcher is in effect traversing a tree because, as noted, the file system does have a tree structure, and this structure is recursive. So all I mean by that is, if you look at the tree that constitutes the file system, if you take the subtrees, they are also obviously trees. So a recursive structure is one whose parts have the same structure as the whole. And these sorts of structures are perfect for the fork join framework. Because what the framework allows you and me to do at the programmer level is to say, here's a problem, and as you're trying to solve this problem, let me point out subproblems that could be dealt with recursively, that is, in the same way. So it's a high-level approach. Now, let me talk a little bit about the fork and join in the terminology. We've seen fork before, of course, but in the context of multiprocessing. In the Java case, the fork-join framework deals with threads, not processes. So the fork refers to forking a new thread, and the join refers to aggregating the results of various threads and bringing them together. So looked at from a high-level view, what's going to happen is this. We're going to search the file system for certain files. We're going to tell the Java runtime how this problem can be decomposed. In effect, we're going to tell it, look at any time we hit a directory, that constitutes a subproblem. Please allocate a new worker thread to handle that subproblem. And then at the end, we want to aggregate all of the files that have been found, and we're going to put them in a list, as you might expect, and then the program is going to print out that list. Now, let me talk a little bit about the technical details. So you're familiar, I'm sure, from having done some recursive programming, perhaps in courses, perhaps in production. So in recursive style programming, we talk about a base case and a recursive case. So let me describe what these are in the file searcher program. So the base case occurs when the file searcher finds a file that is a non-directory. And in particular, we're looking for files that end with a specified extension. So in this example, text files, but clearly anything would do. In this case, the program simply adds that file to a list. The recursive case occurs when we encounter a subdirectory, because then, in effect, we can tell the fork-join framework, here's a subproblem, a subtask if you like. Please allocate a new thread to handle this subproblem, and then behave as you've been behaving so far. Let me end with one final note about the attractiveness of the fork-join framework. When you have a file system, some subdirectories may be very shallow, other subdirectories may be very deep. Some subdirectories have perhaps no files, other subdirectories have many, many, many files. One of the things that the fork-join framework tries to do, in their jargon, is to steal work. So imagine two threads, one looking at a shallow subdirectory, the other looking at a very deep subdirectory. The thread looking at the very shallow subdirectory is going to be done with its job really quickly, and so the runtime is going to let that thread steal some of the work from the thread that's looking at the deep directory. So under the hood, there's an effort in the fork-join framework to ensure that there is an efficient search. Well, this is the overview of the file searcher program. What we'll do in the next lesson is look at the source code. In this lesson, we're going to take a look at the source code for the Filesearcher program, which uses the fork join framework in Java, a high-level framework for doing concurrent programming. The concurrency comes from multithreading, but as you'll see, all of the multithreading is under the hood. We're going to take a very high-level view in this program. So the documentation at the top, as usual, shows how the program can be compiled and run. So there are two classes in the file, and the application file is main.fs for Filesearcher. At line 0, you see an import for the recursive task. This is the centerpiece of the fork join framework in this application. So let me show this right away. The Filesearcher class, as you can see, extends the recursive task. And the recursive task in this case is to return a list of strings, and those strings are going to be files with the specified extension. So in this case, .txt files. Now let's get into the details. I have two fields here. The path is where the search is going to begin in the file system, and the extension then is the desired extension. So for this sample run, we're going to use .txt. The constructor just takes its two arguments and stores those in the fields. The important method for us, marked here with the override, down here at line 3, is compute. So compute is going to return, in this case, a list of strings, which again are these file names. So I'm using an array list as an implementation. And I have an array here, which is going to get me a list of files to be examined. If there are no files to be examined here at line 5, we're done. So for example, if we happen to specify a directory that has nothing in it, then the job is already done. We've hit a base case. In the more usual case, what we're going to do is proceed. So I'm going to maintain a list of tasks, and these are all file searching tasks. In other words, the initial task is a file searcher task, and down here, the subtasks are also, in effect, file searcher tasks. Under the hood, in other words, compute is going to be called recursively, but as you're going to see, there's no explicit recursion in my code. The next step then, at line 7, is to iterate across the files that we've found in the root directory, whatever that happens to be in this example. Java has nice support for this sort of thing, so I get the absolute path of the file, and then basically check the following. If the file is a directory, this is now the recursive case, we generate a new file searcher task associated with this new subdirectory, basically, and task 4 is the key point here in the fork join framework. What we do is announce to the framework that we have found a subtask suitable for recursive treatment. And the runtime is now going to take over. It's going to allocate a thread from a thread pool. So as you can imagine, under the hood, there's an executor service. And then, for bookkeeping purposes, down here at line 12, I add the task to my list of tasks, because later on, I'm going to have to aggregate all of the results. So once we've iterated over all of the files, we're going to assemble the results. So this is the aggregation step, basically. And there's a utility method down here that does this. So it takes a list of strings and a list of tasks, and it iterates over the tasks and basically gets the result from each task and then adds that result to the list of strings. So basically, what I'm doing here is aggregating the results from all of the threads that have found all of the files with a .txt extension. Very clean, very high level. The main class, main.fs, encapsulates main, of course, and it just gets the ball rolling. Otherwise, it doesn't do much. So we create a file searcher. I'm going to proceed from the user's home directory rather than from the system root directory, because it just takes too long, frankly, even on my laptop machine. And as noted, I'm looking for files that end with .txt. So this is easily changeable, of course. And I'm calling compute on that. So that begins the recursive task, and then the subtasks flow from that. When we're all done, when all of those worker threads have finished doing their work, we can print out the results, and I do that in a simple for loop. Let's move now to the command line to see this in action. So I've already compiled the code, and now I'm going to execute it. So I'm in my home directory. I'm going to run java main fs, and it's going to go fairly quickly. And as you can see, from all of the output up here at the top, many of the .txt files I get are log files from my Tomcat. So what I need to do is go in there and clean out that subdirectory at some point. And then I get some other things, web apps and so forth, further up in the output. So for example, if we did a more on this, you can see that I'm picking up some of the materials that are working files for this series of lessons. So there's lots and lots and lots of .txt files, as you might guess, all sorts of them. They're all over the place. So it's a nice rich example for this particular application. I'd highly recommend, if you have time, to give a look at the fork join framework in Java. It's one of the nicest features for concurrent programming that I've seen. This lesson introduces another example of multi-threaded programming in Java, but this example differs in style from the ones that we've seen so far. The working file is async-job.java. You're looking at that in my Emacs editor, and I'll run the program shortly. For now, let's focus on the difference in style by looking at the imports. So at line 1, the cursor is right at the beginning of that line, you see the callable interface. Callable is similar to runnable. We've seen already that the runnable interface declares a single method, public void run, no arguments. The important thing is that run does not return a value. Callable also declares a single method, call, but it does return a value. So callable is a bit more flexible than runnable. The second import of interest is future, and future represents the eventual result of an asynchronous computation. That's quite a mouthful, so let me try to clarify. Normally, when we call a method, what we do is wait until the method returns, perhaps with some value, and then proceed. With a future, it's a bit different. We basically register a computation with the system and say, please allocate a thread to go off and do this, but I'm not going to wait for the computation to complete. Further details will become clear when we look at the actual source code. The executor service and executors we've seen already, so I'm going to pass over those and move down to line 4, which is the main class. Public class async job implements callable. The parameterized type, in this case long, represents the type of value that call is going to return. So call is very flexible. We don't have to return a long. We could return arbitrarily rich data types, lists of lists, maps, that sort of thing. But in this case, we're returning a long value, and the call method doesn't do anything very exciting. It simply goes into a for loop and sums up the result 999. So it iterates 1,000 times and returns the sum. Now, let's move down to main. So in main, you can see I have two local variables, pool size, which I've set to 10. That's going to be the recommended size of the worker pool when we use the executor service. And n, which is set to 20,000, that's the number of jobs that we're going to start. So it's a relatively high number. So we have lots of jobs, but relatively few worker threads to do those jobs. Line 6 is the by now familiar executor service line. So I'm going to create a fixed thread pool of pool size. Again, that's 10. And then I'm going to create a list, called job list, of course, of all of the futures. In effect, all of the asynchronous results that I expect. And I'm just using an array list for that task. So the list, of course, is initially empty. Line 8 is where the action begins. So we create a new job. The data type again is callable long because the call method is going to return a long. And of course, the runtime data type, as you can see, is async job. So that's an instance of the class back up there at line 4. We then take the job and submit it to the executor. We don't call, by the way, you'll notice execute, but rather submit. So we're giving this job to the executor. The executor is going to grab a thread from the thread pool to do the job. Submit is going to return a pending job. And we put that pending job, as you can see at line 10, in our list of jobs. So eventually what we'll have to do is check those jobs for any results. Now in this example, the computations are relatively straightforward, so we're going to expect to get a result from every one of these jobs. But this loop creates 20,000 jobs, which are put into a list, and later on we'll look for the values. And that later on occurs here. So there's a sum initialized to 0, and we're going to go through a for each loop now and basically look at each result in the job list. And for each result, we're going to get the job. So we get the job's result. In this case, it's an integer value. We add it to the running sum. At this point, we can close down the executor service. We're not going to need the thread pool and all of the other resources to go into that anymore. And then print out the size of the list, which is 20,000, and the ultimate sum. And for convenience, I've formatted that output down below, so it's 9 billion and change. Now let me run this from the command line. So I'm going to go out to the bash shell, and let me clear the screen here, and do Java main AJ is the compiled version of the asynchronous jobs. And as you can see, it comes back very fast. This is a multiprocessor machine. The jobs in question are relatively trivial, some integer values, and with a thread pool size of even 10, we have sufficient resources to do this pretty quickly. So this is a relatively new style of concurrent programming in Java. It's not been around from the start, but it's the kind of style that may fit a particular application that you have. In this lesson, we're going to focus on strategies for doing thread-safe concurrent programming. There are 2 examples. Both are in Java, but the strategies would hold across programming languages. So Java is being used for convenience. In my Emacs editor, you're looking at the first of the 2 working files. This is called tempconvert.java. It's a SOAP-based web service. That detail isn't so important to us. What is important is that this web service would be deployed with a web server, such as Tomcat or Jetty, and the 1 thread per request model that we've discussed earlier would pertain. In other words, the web service, in this case tempconvert, consists of 2 operations. I'll come back to those in a moment. And every single request for those operations would be delegated to a separate thread. So we would have, at the web server level, multithreading. It's not multithreading that we cause, but it's multithreading that we need to be concerned about. Now, the 2 operations are the standard temperature conversion operations, centigrade to Fahrenheit and Fahrenheit to centigrade. Again, the details are not so important to us. What's important is the big picture. C to F and F to C in this example are so-called pure functions. That is, they are side effect free. They rely only on arguments passed in each case a single argument, a temperature to be converted. And all of the work is done with that parameter. There are no fields. That's a giveaway in Java, that we're probably dealing with pure functions. There are no side effects. Now, in real-world examples, of course, it's not always possible to write pure functions. It's not always possible to have Java programs in which methods are side effect free. That would be very, very difficult to do, and it might be prohibitively difficult in a real-world application. But a pure function remains an ideal for avoiding multi-threading issues. In other words, a pure function in and of itself is thread safe. Let me now turn to the second example. And this example is a bit richer, and it points to another strategy which has been popularized recently in the Clojure programming language. Clojure is a modern Lisp. Its source code is translated into Java bytecodes, and it runs on the Java virtual machine. So it runs in a multi-threaded environment. Clojure programs have full access to all of the standard Java libraries, all of the data structures, and so forth. What we're interested in is the approach that Clojure takes. So let me start by talking about immutable data types, because if you've used Java at all, you're familiar with at least one of them. So I have a very simple example here at the top of immutable rgb.java. That's the working file, and I'll explain that momentarily. So we create a string. It consists of two characters, uppercase H, uppercase I. We print it out. We get the expected result. And then we call two lowercase on that string, and we store the result in a second object reference, S2, because two lowercase, like all string methods, does not change the string. What it does is makes a copy and changes the copy. So if you were to print S1 out again, you'd get uppercase hi once more. And of course, if you print out S2, you'd get what you'd expect. You'd get the lowercase version of the greeting. Now, the punchline for this strategy is that instances of immutable data types are thread safe. We don't have to do anything. We don't have to worry about synchronization. The problem is basically pushed away. So the example I'm going to use is immutable RGB for red, green, blue. So basically, this is a sort of GIF image class, you might say. So let me get to the API. There is, of course, a constructor, as you'd expect. It's a 4-argument constructor, and the 3 arguments that are numeric are in order: the red value, the green value, the blue value. They have to range between 0 and 255. There's an integrity check on that. And the last argument is a name. So the values you see there are for slate gray. There's an invert method that basically inverts the immutable RGB. We'll see how that's done momentarily. That makes a copy, as you might expect. It does not change the original image. It makes a copy, and the copy is what's changed. So it behaves like a string. There's getRGB, which stores the 3 numeric values in a single int. An int in Java is 32 bits. Each of the numeric values can be stored in 8 bits, so we have room to spare. And there's also getName. So as noted, this is basically the approach that Clojure takes. And if I could do a general characterization of Clojure, it would be this. In Java, most data types are mutable. In particular, types for data structures, lists and maps and that sort of thing. And the exception are the immutable types, and a string is an example. In Clojure, it's quite the opposite. The rule is that the data structure is immutable, and then there are very, very few exceptions, basically 4. If you're interested in Clojure, I've got the URL there. But now let's move on to the RGB class. So here's the constructor. Basically, it just stores the values in local fields. There is, at the top, an integrity check to make sure the values are in range between 0 and 255. There's the getRGB that we saw before. GetName, very simple. The interesting one is the invert, because notice, invert creates a brand new image, just inverts the RGB values, and then returns those, and it changes the name from, in our example, slate gray to inverse of slate gray. And there's the private check down below. Now, immutable data types have a wonderful upside. The instances of these types are automatically thread safe. But these types also have a downside, and that's expense. So if you think, for example, of a list in Java, a normal list, an array list, for example, if you add something to the list, you're changing the original list. The list is mutable. If you remove something, if you change the order of the elements and so forth, you're changing one and the same list. In Clojure, by contrast, if you add even a single element to a list, you're getting back a copy of the original list. And as you can imagine, efficiency now becomes a major concern. In summary, pure functions and immutable types are strategies for writing thread-safe code in a concurrent programming environment, but each has downsides. Pure functions may be too simple for the demands of a real-world application, and immutable data types, particularly types for data structures such as lists and maps, may be prohibitively expensive to use in large applications. But the strategies are certainly worth keeping in mind. This lesson is a wrap-up of the various examples we've seen recently. There have been a lot of examples. They've introduced new features. They've had technical details. So the idea now is to take a step back and look at the big picture, the general results that will be useful as we move forward. The working file you're looking at is wrappup.txt, and I've bulleted the different examples. So let's start with the producer-consumer example that used the BlockingQueue interface and the synchronous queue from the java.util.concurrent package. So the idea is this. The producer puts something in the queue. The consumer takes something from the queue. The queue is synchronous in the sense that the producer blocks on a put operation until a consumer performs a take operation. So another way of looking at this is the underlying queue has no buffering. So the synchronous queue behaves like a pipe. Now the important thing is this. In the example, there were two producers and a single consumer, but there was no explicit synchronization because all of the needed synchronization is in the data type, in the synchronous queue type. Another way of looking at this is to say that what Java provides in the synchronous queue and in some related data types is a thread-safe channel. It's a way for threads to communicate safely without having to synchronize access to the channel. When we look at some later examples in the Go language, we'll see that the thread-safe channel is a really popular mechanism for communication safely among threads. Let's turn next to the Filesearcher program, which illustrated the fork join framework in Java. This framework is designed to implement divide and conquer algorithms. And the example we used is a fairly familiar one. We want to search the file system for files with a particular extension. In our case, it was .txt. And this is a recursive task because the file system is a big tree. You have files that are directories. Directories contain other files. So basically, you have a tree structure. It can be arbitrarily broad, arbitrarily deep, and the Java fork join framework is suited ideally for this kind of task. So the idea is the following. We start at a designated place in the file system. We'll call that the root. And if the root directory contains a subdirectory, we fork a thread to handle that subtask. If we encounter a file that is not a directory file, we check its extension. If it's what we're looking for, in this case a .txt file, we put it in our list and proceed. There's no explicit creating of threads in this, however, because under the hood, the fork join framework uses the executor service. So the executor service does the thread management, and it does so in a fairly sophisticated way. If a particular thread is not doing too much work, let's say it was processing a very shallow subdirectory, it got done quickly. Another thread is doing a lot of work. It's looking at a very deep, very broad subtree. Then the system will steal work from the busy thread and give it to the less busy thread. So it's a high-level framework, but it's also an efficient one. The next example we looked at was the ski rental example, and it used semaphores. So semaphores are ideal for a situation in which you need to limit access to a resource, but you don't need mutual exclusion. So it's not basically one or none. It's we can let in n, but we cannot let in n plus 1 threads. So in this example, we have an inventory of ski pairs to rent, 150, whatever. We decide to keep some in reserve in all cases, in case the big wigs show up. So what we do is create a counting semaphore with a value of 145, and basically what that does is all of the required bookkeeping to ensure that we don't rent out too many ski pairs. So all of the management is basically done by the semaphore, a high-level, very sophisticated construct. A much shorter example illustrated asynchronous multithreading using futures. And the idea here is fairly intuitive. What we do is we dispatch a task to a thread, again using an executor service, but we don't wait, so we don't block, you might say, until that thread does its work and returns something. Instead, we move on to do something else and check back later for a result. So the callable and future interfaces in Java are very nicely suited for this style of programming. We then moved to two idealized approaches to thread safety. I call them idealized because in actual programming, some compromise is going to be necessary. So let's take these in order. So the two approaches, the two strategies, if you like, are immutable data types, heavily used in the Clojure language as noted, and pure functions. And pure functions are an ideal, for example, in so-called service-oriented architectures. So the appealing thing about both is that immutable data types and pure functions are thread safe. So if you had only those in your program, you wouldn't need to worry about thread safety, even if you were in a concurrent environment. The problems, of course, are these. There's a cost to immutable types, particularly data structure types. So for example, if I have a map, let's say it's a big map, there's hundreds of thousands of entries in that map, and I do a delete, the original map is not changed, a copy is made of the map, the copy is changed. So there certainly is an efficiency issue when it comes to immutable data types. With pure functions, the situation is similar. That is, reality intrudes its ugly head. Pure functions are ones that have no side effects. That is, they work only on parameters and local variables. So in the Java case, for example, a pure function would not access a field. The problem is, in real life, it can be very, very difficult to write a program that uses only pure functions. Indeed, this has been a research agenda for a long time. People aspire to do this. It's certainly a worthwhile strategy. It's just not clear that in day-to-day programming, all of the functions we write are going to be pure functions. This lesson introduces a programming exercise. The exercise brings together many of the themes that we've seen in recent code examples. The exercise also looks forward to some forthcoming code examples. Let's begin with an overview. As you can see, I've got 4 bullet points in the working file exercisepc.txt, and the 4 bullet points at the top summarize the themes that we want to pursue in the exercise. So to begin, there's going to be a division of labor through multithreading rather than multiprocessing. We want the threads, of course, to execute concurrently. All of the threads are executing together. The threads need to cooperate because their labor is going to contribute to a common goal. So there's a task that all of the threads are working towards. The threads need to share information, and we want to do this in a thread-safe way to make sure we avoid race conditions. Now let me get into some detail. I've got a depiction of the producer-consumer pattern that the exercise emphasizes. So we're going to have producer threads send data items into a thread-safe channel, and a consumer, in this case, is going to read those data items out of the channel. Let me give a realistic example, and then we'll simplify that example for the purposes of the exercise. Suppose that these producing threads are searching the web for information. Since they're searching the web, they're going off machine. This is going to be time-consuming. Search, of course, is inherently time-consuming, and it's going to take a while for them to get the data items to send to the consumer, which in this case we might assume does an analysis. So, for example, the producers might be looking for a name in news stories, for instance, and the consumer might do a frequency count of the occurrence of various names. One consumer might do. In any case, you might have fewer consumers than producers because the consumer work is not so time-consuming. Now, to keep this simple, What I want to do is have the producing threads produce their data rather than search for their data. So let me jump down to this second simple depiction. The producing threads are going to generate positive integer values. And you might consider putting in some random sleeps in order to get a more realistic scenario. And you should decide there should be at least a couple of producing threads, but you could have as many as you like. They're going to generate these positive ints, and they're going to send them over a thread-safe channel to another thread, and that thread is going to test for primeness. If you want something simpler, any numeric property would do. For example, the consumer might test whether the value is even or odd, whatever you like. The important thing, of course, is the use of the thread-safe channel. So there's one channel in which producing threads send information to a consuming thread. Let's start with 1 to begin. And then the consuming thread itself is going to become a producer. It's going to take the prime numbers that are sent to it, and it's going to send them over a thread-safe channel to another consumer who is going to aggregate these results and then do a sort. And, for example, print out the sorted list to the screen. The important thing is that we have multiple threads at work. We have multiple producers in one case and a single consumer. And then we have a single producer, the consumer from just before, sending information to another consumer, the sorter. Java has very, very nice support for thread-safe channels. So java.util.concurrent, of course, is the package that has all of the goodies. And we've already seen the BlockingQueue at work. So you might take a look and decide what would be the appropriate sort of channel to use for this exercise. You'll also find that this exercise will be helpful when we move into the next set of code examples, which are going to involve the Go programming language, because Go puts great emphasis on thread-safe channels. In any case, I hope that you have a chance to do this exercise. I think you'll find it instructive and useful. This lesson is preparation for some forthcoming code examples. Let's take a step back and look at the big picture before we jump into the code. What we've seen so far in the C and Java examples are two basic approaches to thread coordination. The first approach we saw is the basic mutex approach. We saw this in the Miser-Spendthrift application in both C and Java, and indeed we've seen several variations of it. And here's a quick depiction of how this works. We have a memory location n. In this case, it's depicted as holding the value 7. And we've got multiple threads in the same process, all of which, of course, thereby have access to this location. The idea behind the basic mutex approach, of course, is to have a lock on that location so that at most one thread at any time can grab the lock and hold the lock and thereby gain access to the memory location. Other threads are effectively blocked. So this is the idea behind mutual exclusion via locks protecting critical section code. And as noted, we've seen several examples of this. We've also seen higher level approaches to this that use explicit locking under the hood. So, for example, the Java atomic integer type is a fine example of this. The synchronization, the mutual exclusion, is baked into the underlying methods of the data type. Now, there's an alternative approach. We've seen it a bit already. It's the thread-safe channel approach. We've seen that in Java, but we're going to see it in forthcoming examples in the Go language. So I'm going to call this the thread-safe channel approach. And the idea here is that we're going to have, once again, multiple threads. We're going to have shared memory locations to which all of the threads are going to have access. We're going to have concurrent thread execution. And as we know, the scene is now set for race conditions. And the question is, how do we avoid the race conditions? So in this example, we're going to have a designated thread. I'm going to call it both the N controller and the N thread for emphasis. And that thread is going to have sole access to the memory location N, but it's not going to use explicit locking to do so. This is going to be a matter of program design. Another way of looking at this is that the N controller or the N thread is going to treat N as if it were. It isn't, but as if it were local storage for the N thread. So, in other words, part of a particular thread's stack, if you want to get down into the implementation detail. But again, the key point is that we're not going to do any explicit locking. Now, other threads that need to gain access to N do so through a thread-safe channel. So the access is now deliberately indirect rather than direct. And down here at the very bottom of optionsoverview.txt, that's the working file, there's a depiction. So the idea is the N thread, shown here roughly in the middle of the screen, has sole access to the memory location N, again shown as holding 7, and other threads use a channel to send information to the N thread. I'm showing the channel as bidirectional because the N thread may want to respond back. For example, if a thread is going to increment N, the N thread might send back the incremented value. If a thread is going to decrement N, the N thread might send back the decremented value. So the communication can be two-way for flexibility. The important thing, though, is that the thread-safe channel does the heavy lifting required in synchronization. We avoid explicit locking, and we rely instead on the channel to serialize requests that we get from the other threads. The N thread then reads these requests one at a time, takes whatever action is appropriate, and then perhaps communicates back to the thread that sent the original request message. Basically, this is the style of programming we're going to move on to when we look at the Go programming language. To be sure, this style is also possible in Java and other languages, but looking at it across languages will emphasize the commonality of the approach. So this approach may be emphasized in one language more than another. The API may be different in one language than another. The critical thing is that the underlying approach is common, and that approach is to avoid explicit locking, the mutex approach, I've been calling it here, and to rely instead on thread-safe communication among threads. This lesson is preparation for the next two code examples, both of which are in the relatively new programming language Go. So let me begin with a bit of motivation. Let me explain why we're looking at yet another programming language. By the way, there's no assumption that you've any background in Go or even any interest in learning the syntax of the language. We're more interested in modern approaches to multithreading, and these approaches have the following in common. They want to combine efficiency with a high-level API for the programmer so that the programmer can ignore, as far as possible, low-level implementation details. Now, let me go back to the Java Executor service and just review a couple of points about that service, because that's a representative of a modern high-level approach to multithreading. So, as you'll recall, with the Executor service, the system has a pool of threads. It might grow and shrink dynamically, might be fixed in size from the start. In any case, there's a pool of threads and runnable objects at the API level. In other words, objects whose classes implement the run method are multiplexed onto this pool. So a particular runnable may be assigned this thread for a while. Maybe it goes off and does some I/O, comes back, and then gets assigned a different thread a bit later. All of that is under the hood. It's not something that we as programmers need to worry about or even know about. The upshot is that the programmer gets to focus on application logic, not on implementation details, and this separation of concerns does two wonderful things. It provides an efficient implementation of multithreading, and it allows us to ignore a lot of the grimy details of multithreading. The motivation behind the Go language is very much the same, and the core construct in Go for multithreading, or more accurately for concurrency, is the Goroutine. So the multithreading is at the implementation level, the Goroutine is at the API level. Let me give you two examples at the source code level. So you see Go list sort. This is a sort of object-oriented syntax that we're familiar with from Java. Basically, this says execute the list sort function concurrently. And as you might expect, that sort function is a library function. The second example, Go foo, executes the user-defined function foo concurrently. Go, by the way, does support anonymous functions, so you don't actually have to call Go on a named function. You could define the function in effect in place. Now, Goroutines have their own scratchpad storage. In that respect, they're similar to threads. But the key point is that Goroutines are multiplexed onto threads. So multiple Goroutines can share the same thread. A given Goroutine may be executed as different threads over its lifetime. And in fact, they've done some extensive testing here. You can have significantly more Goroutines than native threads under the hood. So Goroutines are very much like Java executors in the sense that they are a high-level way of doing multithreading while hiding many of the grimy details of multithreading. Now let me turn to channels and say right at the start that Go does have locks, mutexes, so you can do conventional locking in Go, and sometimes that's the best way to go. Sorry about that pun, unavoidable. And we're going to see an example of that a bit later. But one way for Goroutines to communicate with one another is over thread-safe queues in Go. These are called simply channels, and we'll see examples of these as well. A feature that I like quite a bit is that the channels come in two flavors. You can have a buffered channel, which allows, for example, a writer to write something to the channel and then move on. You can have an unbuffered channel in which a writer blocks until the reader reads from the channel. So you get two flavors of channels, and each is very easy to use at the syntax level. We'll see that a bit later. Now let me turn to the examples and just provide a little bit of background. I'm going to do two examples of the Miser-Spendthrift code. In the first, I'm going to use mutexes, and the second, no mutexes, instead thread-safe channels. There is one difference. I'm going to have many Goroutines accessing the account balance, but I'm not going to ensure that the balance winds up at 0 at the end, because I'm going to allow misers to save randomly generated amounts, and I'm going to allow spendthrifts to withdraw randomly generated amounts. So we might wind up, for example, with either a lot of cash in the account or not enough cash in the account, and we'll let the bankers work that out. So, as noted here at the end, the account balance is going to be allowed to go negative or positive, and we'll see sample runs, as you might expect, of this code. This lesson examines the first of two programming examples in Go. The examples are variations on the Miser-Spendthrift programs that we've seen in C and Java. So here are the differences. Instead of a single miser and a single spendthrift, we're now going to have 100 misers and 100 spendthrifts, and each one of them is going to do its thing 1,000 times. The misers and the spendthrifts are going to be implemented as Goroutines. Further, the increments and the decrements to the account balance are no longer by 1. Instead, they're by a randomly generated value. As a result, the balance need not, in fact, almost for sure, does not wind up as 0. So it's going to be positive or negative and probably different each time the program is run. Before we jump into the source code, let's go to the command line. So you're looking at my bash shell, and I'm going to do a run. How to run is part of the documentation. So I'm going to do a run. We wind up with a negative account balance. So basically the spendthrift won this time. This time we get a positive account balance, and so the miser wins. The source code does, by the way, have commented out reports on each and every increment and decrement, so I'll point those out when we return to the code. So let's go back to the Emacs editor. The source file is ms1.go. Up here in this comment is instructions on how to compile and run. So go run. If you give it the source file, it's first compiled and then executed. So Go is a language that does compilation to native code. There are some peculiarities in the syntax of Go, and let me come down here and just point one of them out right here. So you see there's a function called report. It's got two parameters. The first is a string, the second is a 32-bit int, and you'll notice that the parameter name precedes the data type. In Java and C, of course, the order would be reversed. You'd have the data type and then the identifier. So this is one of the features that distinguish Go syntax. So let me jump down here. And this is where the code becomes interesting for us. So we have an account balance. It's a 32-bit integer initialized to 0. That's at line 1. We've got a mutex, a lock, at line 2, and you'll see the syntax for this is absolutely straightforward. Increments and decrements record the total amount of increments and the total amount of decrements to the balance. So this is for reporting purposes. Go routine count is set to 100, so there's going to be 100 misers and 100 spendthrifts instead of one of each. The maximum amount randomly generated is 5. So basically, we're going to get values between 0 and 5. To make sure that we never have a 0, I'm going to add 1 to that amount. And each Go routine is going to do its thing 1,000 times. The wait group, which is one of the library types in the Go language, basically ensures that main waits for the Go routines to do their thing before main issues a final report. So we've seen this sort of thing in C and Java already. So here's a loop that basically generates the misers, and there's a similar loop that generates the spendthrifts. So we'll focus on the miser loop because they're basically the same. So we're going to go into the for loop and we're going to iterate 100 times. Each time we're going to basically say we want to wait on the following Go routine. And that Go routine occurs at line 5. So you see Go, and recall that in this language, when you say Go and give it a function, you're basically saying to the runtime, you can execute this function concurrently. This particular function is anonymous. It's unnamed. You could also have a named function. So basically, it's being defined in place. And the important detail is this. We go into a loop, so each of these miser Go routines is going to do this. It's going to loop 1,000 times. Each time, it's going to generate a random value. And now we get to the critical section code. You can see the API is high level and straightforward. We do a lock, we increment the balance, we release the lock. So what we have here is traditional explicit locking. It ensures mutual exclusion. Down here, this is a library function, atomic.addInt32. The locking is baked into the data type, and this is used in this particular example to keep a running count of how many increments have been made, or I should say, the total amount of the increments. This is another library function. Basically, it's a yield. So each of the Go routines is playing nicely. It's doing its thing, and it's saying to the runtime, if some other Go routine would like to go, by all means, please let it do so. The spendthrift code is essentially the same. The only difference, of course, is that instead of incrementing the balance, spendthrift is going to decrement the balance. So once those Go routines have done their thing, the wait call here ensures that the main Go routine waits for the misers and spendthrifts to finish. A report is generated, and it's straightforward. What the balance is, the total amount of increments, the total amount of decrements, and then as an integrity check, the difference between the increments and the decrements, and that, of course, should match the balance. Now, the API here is relatively straightforward. It's a bit simpler than what we've seen in either C or Java, but you can see that the idea is essentially the same. A Go routine grabs a lock, it executes critical section code in single-threaded mode, releases the lock, and then moves on. This lesson covers the second programming example in the Go programming language. You're looking at the source code in my Emacs editor. The name of the file is ms2.go, and we'll compile and execute it shortly. Let me begin with an overview of the similarities and differences between the two programs. Each program has 100 misers and 100 spendthrifts implemented as Goroutines. And each of these Goroutines iterates 1,000 times, so it does its work 1,000 times. The misers, of course, increment the account balance, and the spendthrifts decrement the account balance, but they do so by randomly generated values. So the end result is not going to be an account balance of 0, even though the balance starts out with 0. Where the two programs differ significantly is in how they avoid race conditions. So in the first program, a mutex is used. There's explicit locking of the critical section code, and that code, of course, is the incrementing of the balance by the miser and the decrementing of the balance by the spendthrift. This changes dramatically in the second example. What we now have, in effect, is another player, a banker. The banker is implemented as a Goroutine, and it's the banker alone that touches the account balance. So the banker does all increment and decrement operations. The misers and the spendthrifts, by contrast, send requests to the banker to increment or decrement. And those requests are automatically serialized over a channel, and the banker reads those requests from the channel, does the required operation, and then communicates back to either the miser or the spendthrift through another channel. So in effect, mutexes give way to thread-safe channels. Now, let me run the program first, and then we'll return to the source code and do a more careful analysis. So once again, from the command line, you can compile and execute it once with go run and the name of the source file, in this case ms2go. And you can see in this case, it's the misers who won. The final balance is 160. And this time the spendthrifts won, and so on. So the behavior at the UI level is essentially the same. Now let me return to the source code, and we'll look at the difference in the implementation. So the first sign of a difference occurs at lines 1 and 2. So there are two structures. One is called miser-op, that represents a miser operation, and the other at line 2 is a spendthrift op, and that of course represents a spendthrift operation. Let's look at the miser operation, since the spendthrift is in effect a mirror image. The miser sends an instance of a miser-op structure, which contains two fields. The first field is an increment, which is an integer value. And again, this is going to be 1 to 5, let's say dollars, euros, or whatever currency we happen to be using. And the second member is a channel that allows the banker to respond back. The syntax is a little bit strange on a first look, but that's basically what we have: an amount to send and a channel through which the banker can respond to a miser. The only difference then in the spendthrift structure, of course, is that there is a decrement rather than an increment. Now, basically, everything else is pretty much the same as far as variables go. There's the balance initialized to 0. I keep track of the total number of increments and decrements to do an integrity check at the end. I call this limit. A better name for this would be the number of times that the Goroutines loop. The maximum amount in this case is set to 4. So 0 to 4 are the possible increment and decrement values. The iterations per miser and spendthrift is 1,000. So each Goroutine is going to do its thing 1,000 times. We have the wait group before, and then the buffer size I'll get to momentarily. Now, here are the two thread-safe channels through which misers and spendthrifts communicate with the banker. The first is called deposits at line 3, the second withdrawals at line 4. And again, let's not look too closely at the syntax. We're not trying to learn Go. We're trying to get a high-level view of the options that the Go language gives us for thread communication. So basically, each of these channels is buffered, and the buffer size in this case is 2. A buffered channel is, in effect, a non-blocking channel. In other words, the channel has two slots that can be filled. So a miser could, for example, send a miser operation to the deposits channel. Another could do the same and continue on their way. Once the buffer size is reached, however, the operations become blocking. In other words, the next miser that tries to send a message to that channel is going to have to wait until one of the messages in the now full channel is taken out. Now let's get to the players. So we've talked a little bit about the misers and the spendthrifts. Those again are implemented as Goroutines. This Goroutine represents the banker. So you see Go, and then again there is an unnamed function. This function sits in a loop, that's the for loop, and executes a select. A select is an inherently non-blocking structure in Go, and the basic idea is this. The banker waits for two things to happen. The first thing to happen, or one of the two things to happen, is that a miser makes a deposit. That's covered by the first case starting at line 5. At line 7, the second possibility is that a spendthrift makes a withdrawal. Now let's go back to the deposit. When a deposit comes in from a channel, what the banker does is increments the balance by that amount. Notice, by the way, there is no explicit locking. We don't need it because it's only the banker. It's only this Goroutine that ever updates the balance. And then what the banker does is responds to the miser who just made the update, with the new balance. So in effect, what the banker is doing is sending back a confirmation. Here's the new balance. And you have similar logic for withdrawals, which are done by spendthrifts. The miser and spendthrift routines, again, are essentially the same. Again, each of these is implemented as a Goroutine, and that Goroutine for the misers starts here. The logic is very similar, except in the part that starts at line 9. In the first version, we had a mutex, explicit locking. Now we have something different. We basically create a miser operation. That's this line, 9. We send that deposit request to the banker, and then we get the new balance back from the banker. I've got a Boolean variable. If the report is set to on, I actually give an ongoing report of what's happening to the balance. So if you want to see that, just change the value of report on. It's way back up at the top. Set that to true instead of to false, and you'd get a lot more output. The spendthrift logic, by the way, is essentially the same, and the reporting at the end is essentially the same. In summary then, in the second implementation of the Miser-Spendthrift program, we've gotten rid of the mutexes of explicit locking and replaced that with a banker who maintains two channels, one for deposits, which come from misers, and another for withdrawals, which come from spendthrifts. The banker then does the appropriate thing, updates the balance, either by incrementing or decrementing it, and then uses another channel to respond back to the updating Goroutine. So it's a high-level approach that does not do any explicit locking. So there's no explicit mutexes protecting the balance. This lesson is a review of multithreading as a way to do concurrent programming. We've spent a lot of time on multithreading, looked at lots of code examples in different languages, C, Java, Go, and used those code examples to explore the challenges and the opportunities that come with multithreading. It's appropriate, I think, to have spent so much time on multithreading. It's arguable, in fact, you can make a good case that over the past 10 years or so, multithreading has emerged as the most popular way to do concurrent programming. There are a number of reasons for this. First, and perhaps foremost, multithreading is inherently efficient. We've seen that, and we'll get into some details momentarily. Second, languages such as Java and C# use multithreading as the preferred way to do concurrent programming. Older languages such as C and C++ have benefited, no doubt, from the nice, clean, standardized API that you get with pthread, which we've seen. Let's now go through the upsides and downsides of multi-threading a little more systematically, and then summarize some of the other major points that we've looked at. So the primary upside we've talked about many times, and it comes down to this: thread-level context switches, which occur when one thread is preempted in favor of another. On a processor, thread-level context switches are very, very efficient. In fact, the cost approaches zero. Those switches are far more efficient than process-level context switches. In effect, context switches between two threads in different processes. So what you get with multi-threading is a boost in efficiency, in performance. The primary downside is something that hits us as programmers. Threads within the same process share the same address space. They have access to the same memory locations, which opens the door to race conditions. So the programmer has to be careful to avoid race conditions. The downside of avoiding race conditions is that this opens the door to inefficiency and even deadlock. So let me jump to this sub-bullet point. In order to avoid race conditions and do multi-threading the right way, you have to coordinate threads just enough. In other words, if you don't coordinate enough, and we've seen this in the Miser-Spendthrift examples, you get a race condition. If you do it too much, you get either inefficiency or even deadlock. So there are twin perils associated with multi-threading programming. In short, it's tough on us programmers. Over the past 10 years, there's been lots of research done on multi-threading, and one of the issues that deserves mention here in the summary is that the sky is not the limit when it comes to the number of threads you can have in a multi-threaded program. In other words, at some point, the cost of coordinating threads, synchronizing them properly, that cost becomes prohibitively large. You may reach a point, for example, where the cost of multi-threading approaches the cost of multiprocessing given process-level context switches, which, as we know, are relatively expensive. Now let's get into some details that we've looked at. So one of the big issues, of course, has been how to coordinate threads properly, synchronize them, and we've looked at two general approaches. One might be described as memory location locking using mutexes or semaphores. So we've seen an example with Java semaphores, which are not quite as strict as mutexes. They allow multiple access to important sections of code. But we've emphasized mutexes, which basically lock access to critical section code. Mutexes allow at most one thread at a time to execute such code. So what a mutex gives you, in effect, is single-threaded execution of certain code segments in a multi-threaded environment. Now, we've seen this done with explicit locking. We've seen it in C, in Java, and even in Go. So we've looked at relatively low-level programming constructs, such as the pthread mutex and the Java synchronized block. We've also looked at high-level approaches where the thread synchronization is baked into the data types. So in particular, we've looked at lots of examples from java.util.concurrent, which has excellent support for synchronization built into data types. The atomic integer, the concurrent hash map, the copy on write array list, and so forth. That's really wonderful stuff from a programmer's point of view. The challenge for the implementation of those types, so the concurrent hash map, the copy on write array list, and so on, the challenge is to make sure that instances of those data types run efficiently. And Java has done a very nice job in doing that. The second general approach that we've seen might be described as message passing, and this approach came to the forefront in the last Go example. So we had misers and spendthrifts implemented as Goroutines, which under the hood execute as threads, but we also had a banker as a Goroutine. And basically, the banker was the only Goroutine, and so really, at the implementation level, the only thread to have access to the account's balance. Everything else was done through messages. So a miser would send a message to the banker, a spendthrift would send a message to the banker over thread-safe channels. so we didn't need mutexes. This message passing approach has become popular. There's very good support for it in other languages as well. We've seen it in Java, and it's available in C and C++ and other languages. A final point is to consider some broader issues. So we've looked briefly at immutable data types because instances of immutable data types are inherently thread safe. They're as thread safe, for example, as parameters and local variables. The downside of this approach, which I called the closure approach because Closure has revived interest in this approach, the downside is that immutable data types are relatively expensive. So if you think about a list, for example, if every update to a list requires a copy of that list, then of course, as the list gets larger, the cost becomes greater. So the challenge in the immutable data type approach is to make sure that instances are efficient. And this is tough. Closure has done some ingenious things in this area. The other broad issue we looked at is how multithreading has become higher level at the API level. So we've seen, for example, in the Java executor service with the Go languages Goroutines that thread pools are generated automatically. They're maintained, in effect, by the system's runtime. And at the API level, you and I as programmers can focus on concurrent logic. We don't have to think about, is this concurrent module going to map to this thread or that thread? In effect, we don't care. We leave that implementation detail to the runtime. This, I think, is a significant advantage over the past decade or so in multi-threaded programming. That's a wrap-up, then, of what we've seen in multi-threading. We haven't seen the last of multi-threading. The approach so far has been to look at multiprocessing, multi-threading, and next, non-blocking I/O in isolation. But in the real world, of course, they occur in combination. And so we'll come back to that theme over and over again. So this wrap-up has really covered the isolated look at multi-threading. This lesson presents an overview of non-blocking I/O, and it should be useful in the forthcoming code examples. Let's start with some basics. These 4 sub-bullets present the standard categories for instruction types. We're talking, of course, about compiled instructions. And in some categorizations, you're going to find subtypes, but I've limited the types to 4. So we have arithmetic logic instructions, add, equals, that sort of thing. And on modern systems, these are very, very fast instructions. In fact, most of these are going to take a single tick of the system clock. The exceptions would be, for example, multiplication and division, but in general, arithmetic logic instructions are very fast. The second category, not quite as fast, but still pretty fast, are control instructions. And a typical example would be the if-else test that we're all familiar with. Data movement instructions, and here we mean movement between main memory and the CPU, are not as fast as control or arithmetic logic instructions, but nowadays pretty fast on modern systems, and examples would be load something from memory, store something to memory. Of interest to us is the last category, the I/O instructions, print to the screen, read from a disk, that sort of thing, because these instructions are going to be several orders of magnitude slower, in general, than arithmetic logic instructions. So the I/O instructions are very slow. If a program blocks or waits for an I/O instruction to complete, it's consuming a lot of valuable time. So the obvious questions become, what's the best way to avoid blocking on I/O operations? In other words, what's a nice API for doing non-blocking I/O? And then the related question, of course, is, what should the program do with the time saved by not blocking? And these are issues that we're going to address in the forthcoming code examples. Let me turn now to some issues of terminology. There are various terms used to describe non-blocking I/O. I'm going to favor non-blocking as the term because it's intuitive, it's commonsensical, it's pretty clear. Sometimes you'll hear non-blocking used as a synonym for asynchronous. Sometimes this isn't the case. Whenever I use asynchronous, I'll try to be careful by explaining exactly what I mean by that. But for the most part, I'm going to stick with non-blocking. In order to get a working definition of non-blocking I/O, I'm going to rely on a pair of pseudocode examples that we're going to look at momentarily. And these examples use one of the 4 standard I/O operations. Those operations, of course, are open an I/O device, close an I/O device, read from an I/O device, write to an I/O device. Now, there are obviously other operations on I/O devices. You could do a search and so on, but these are the 4 basic ones. In particular, the examples that we're going to look at focus on the read operation. Let me bring up the examples. The first one, as you can see here, is for blocking I/O, and it's pretty short and sweet. Again, it's in pseudocode, and we'll come back and look at it in a moment. The second one, for non-blocking I/O, is also in pseudocode, but just eyeballing it, you can see that it's much longer, and it is certainly more complicated. There's a loop, there's 2 if constructs, and so on. But the first example has none of that. Very, very simple. I've declared a byte buffer big enough to hold 4 bytes. I'm in a so-called try block. Those of you in Java, C#, C++, and so forth will be familiar with this. If you're not from such a language, the idea is anything in the try block might generate an error, in which case control would jump immediately to the catch block down below. What I don't want to show in these examples are how to handle errors. In this example, the read operation blocks. In other words, we basically sit here at this line until either we've read the 4 requested bytes or an error occurs. Let's suppose that there's no error. We read the 4 bytes. We then proceed, because now the blocking ends, the waiting ends, we proceed to the next line of code, which is to process this buffer in some appropriate way. Let's come down to the non-blocking example and talk about why it's so tricky. Once again, we have the byte buffer. We now have an index. I'm assuming that the first position is 0, so the buffer is indexed starting at 0. The expected count is the number of bytes we expect to get in the read operation, and that, of course, is the buffer size, in this case 4. How many so far keeps track of how many bytes we've accumulated so far, and to begin, of course, the answer is none. Once again, we jump into the try block. We go into a loop because we don't know how many attempts it's going to take to get the 4 bytes that we want. So we do a read. The 3 arguments to the read in this case are the byte buffer, where to start putting the bytes, that's the index, and how many bytes we want to read. And in this case, the first time through, the answer is 4. The read returns immediately. There's no blocking. There's no waiting. There are various possibilities, including the possibility that we got nothing. So if we got nothing, we go back and start looping again to do the same thing over. If we got fewer than the expected bytes, it's a bit trickier. I'm not going to walk through every line here, but you get the idea. I need to update how many bytes I got so far. If I got all of the bytes I needed, I can break. If I didn't get all of the bytes I needed, I need to adjust my expected count. I need to adjust my index, and so on. So there is inherent trickiness here, and that's the whole point of this example. Non-blocking I/O is non-trivial to program. So to sum up, blocking I/O is certainly an easier API. I don't think there's really any doubt about that. But non-blocking I/O brings the benefit of efficiency. We don't have to sit and wait. We can do something in the meantime. And again, the sub-bullets here summarize on those very points. We're going to see all of this in the flesh, as it were, as we look at code examples, and I'm hoping that this overview will provide some context for those examples. In this lesson, we're going to focus on non-blocking I/O as a concurrency mechanism, and we're going to use Node.js as an example. A quick word about Node.js. In recent times, it's fair to say, I think, that no piece of software has brought more attention to non-blocking I/O than Node.js. Node.js, of course, didn't invent non-blocking I/O. It's been around forever, but it has brought it to the forefront yet again. So Node.js is a general-purpose JavaScript implementation. It's based on Google's V8 JavaScript. It's fair to say, however, that Node.js is tailored for web servers, although you could use it for other purposes as well. The real point of interest for us is this. At the API level, which I'll clarify in detail momentarily, a Node.js server is a single-threaded process. It uses non-blocking I/O as its concurrency mechanism. 2 points deserve emphasis. Under the hood, there is multi-threading in the Node.js server. It's just that it doesn't appear at the API level. As we saw in an earlier example, Node.js does have very nice support for multiprocessing with the cluster fork method. Let's get back now to the issue of single-threaded process using non-blocking I/O as a concurrency mechanism. So I have a depiction here in the middle of the file. By the way, the file is nonblockconcur.txt. It's included among the working files. I've tried to keep this depiction as simple as possible. So the big picture is this. I have a double line in roughly the middle of the page. Above the line is the API level, below the line is the implementation level, and the implementation level is the library level. So here's basically how a Node.js server works. You have incoming HTTP requests, and these hit what I'm going to call the event engine. The event engine at the API level does not block on incoming requests or on outgoing responses. What the event engine does is to dispatch each request to a function call. So when we saw multiprocessing in a web server, the web server would dispatch a request to a process, we hope from a process pool, for handling. When we saw multithreading, the web server would dispatch an incoming request to a thread, we hope from a thread pool, for processing. But in this case, we're in a single-threaded environment. So the event engine is basically making a single-threaded function call per incoming request. This is basically the API level, so we can summarize that level by saying we have a single process with a single thread. Now we're going to move down to the implementation level, or if you like, the library level. And the library that Node.js uses under the hood is named libuv. So it's a library that does non-blocking I/O, and libuv maintains a thread pool in particular for long-running jobs. So imagine, for example, an incoming request that requires that we go against a database or even go off machine to hit a web service, that sort of thing. Libuv would dispatch that job to a thread from its thread pool. This is not evident at the API level, but it is at work at the implementation level. Let's do a little bit of summary. Node.js tends to work very, very well when the incoming HTTP requests are small, the application logic is short, and the outgoing HTTP response is likewise reasonably small. It doesn't do as well when there are incoming requests that require a long-running job. In that case, you basically have, for sure, multi-threading under the hood. In summary, Node.js is really good if you have small requests and reasonably small responses, and in many websites that's absolutely the case, and Node.js has proven to be a very powerful tool for building web servers to handle that sort of traffic. The real point of interest for us is this. As we get into the grimy details of non-blocking I/O, it's always good to keep in mind that non-blocking I/O tends to be used in a supplementary mode when it comes to concurrency. You tend not to have non-blocking I/O used as the one and only mechanism to support concurrency. We've seen this, by the way, already. The Nginx web server uses multiprocessing as its primary concurrency mechanism, and it tends to use a small number of worker processes, 4, for example. But those processes use non-blocking I/O under the hood, and this is really powerful because, and this has been studied fairly extensively, with Nginx you may have a single worker being able to handle, for example, 1,000 requests concurrently because of the speed that the non-blocking I/O provides. So non-blocking I/O is an excellent mechanism for concurrency. It just tends not to be the only one in use in production-grade software. This concludes this overview of non-blocking I/O as a concurrency mechanism. We're now going to put this to use in a programming example, but before that, let's take a short pause. This lesson introduces the first code example for non-blocking I/O. The program is called the Epoller program. The document you're looking at in the Emacs editor is Epoller Overview.txt. Let's start out with the central issue addressed in this program. Recall how blocking I/O works. Suppose we do a read operation. One of two possibilities occur. There could be an error, or we could complete the read successfully and move on in the program. With non-blocking I/O, of course, things are much trickier. A call to the read function is going to return immediately, so the obvious question arises, how is the program to determine whether the read succeeded in getting everything that it was supposed to read? There are, in general, two approaches that might be taken. The first is to have the application itself check. We could go into a loop, for example, try to do a read, check to see how many bytes we got. If we didn't get all of the bytes we were looking for, do it again, and so on. So I give the example here of trying to read a 4-byte integer, a pretty trivial example, but it exemplifies the problem. We try to read an integer. If we got all 4 bytes, great, we move on. If not, we try to read whatever bytes we still need to get. The second approach is more common, as you would expect, because that first approach is pretty low level. What the application can do is delegate the low-level work to a library function and interact then with the library function, and the library function is going to provide some sort of notification mechanism. Let me describe two broad approaches for this notification mechanism. One approach is to have the application specify a user-defined function, in effect, a callback function, and to tell the library, here, I want to initiate a non-blocking read. You take over. When the read succeeds, call my function. And, for example, provide the bytes that were going to be read. For reference, let's call this the callback approach. The second approach has some similarities, but it also is slightly different. Once again, the application delegates the work to a library. So the read is still non-blocking. The library then takes over, but at some point, the application waits for notification from the library. Even though most of the I/O calls may be non-blocking, there's a wait call that blocks. And in effect, we're saying to the library, I'm waiting here until you tell me that at least one of my pending operations has succeeded. For reference, I'm going to refer to this as the polling approach. Now, the Epoller example, as the name suggests, takes the polling approach, and here's a depiction of how the application works. So there are two programs involved. The FIFO writer we've actually seen before, and we'll look at it again just for review. The FIFO writer generates positive integer values and sends them to a named pipe. It does some pausing in order to give a more realistic feel to the work. In this particular case, the Epoller program does non-blocking read operations on that named pipe to determine whether there's anything there for it. And what it's trying to do, of course, is to read the ints that are sent to the named pipe, and the named pipe, again, is a FIFO. It's a queue. Once the Epoller reads successfully a 4-byte int, to provide some application logic, what I have the program do is check whether the value is a prime. If it is a prime, the value is printed out and a count is updated. So at the end, we know how many primes we found. And in the current implementation, the FIFO writer is generating 12,000 values, and the Epoller is reading all of those values. Now, there's some details down here that expand on the points that I just made. Let me make a final point. Since we've talked some about Node.js and about the underlying library, libuv, here's a reference for it if you'd like to check this out. What's interesting for our purposes is that libuv on a Linux system gets support from the Epoll library, and that's the library that I'm using in the Epoller application. On a Mac, you might use the KQ library, and Windows also has comparable libraries that we've talked about before. The Epoll library is representative of a modern polling approach to non-blocking I/O, and in the next lesson, we'll look at the source code. In this lesson, we're going to examine the source code for the Epoller program. The Epoller program consists actually of two files. We're looking at one of them. This is FIFO-writer.c, which generates integers and sends them to a FIFO, a named pipe, and the Epoller then does non-blocking reads from that pipe. So here's a very simple depiction for review. We've actually seen the FIFO writer before in another example, but let's do a very quick refresher. The details of this program are not so important. Our interest is in the Epoller part. So there's going to be 3,000 write operations. Each one of those write operations is going to write 4 integers. They're going to be randomly generated. And in between the writes of these chunks of 4, we're going to sleep up to 10 microseconds. So the sleep is in there to give this a slightly more realistic feel. The actual writing occurs down in these nested loops. So here's the outer for loop. It iterates 3,000 times. Here's the inner for loop. It iterates 4 times each time. So we wind up with 12,000 integers. Let me do a sample run. There is a little bit of a complication. I'm on a Mac, and I'm using the Epoll library, which is available on Linux systems, but not on Macs. So I've done a remote login to a Linux system, and I've compiled the code. I'm about to run the FIFO writer in the background. So let me do that now. Now I'm going to run the Epoller, just so we get a sense of how this works. And what the Epoller is doing is reading the integers from the FIFO, determining whether the read integer is a prime number, if so, reporting it to the screen, and keeping a count, which you can see down at the bottom. Out of the 12,000 values generated, there were 604 primes, which is ballpark. Let's return now to the Emacs editor and look at the code that's really of interest to us, which is the Epoller, because this is where the non-blocking I/O occurs, and we'll go through this a bit more carefully. At line 1, you see a function called isPrime. We need some application logic. The idea is the Epoller is going to read an integer from the FIFO. It then should do something with it, and what it does in this case is determines whether it's prime. This code is a little bit grimy, but it's fast and it's effective. So it's correct, I think you'll find, and it does its job pretty quickly. The details are of no interest to us. The function at line 2 is of more interest. What we want to do is create a non-blocking reader. So the way we do this is we start out in a very traditional C-like fashion. We open up the pipe. We then make sure that that worked okay. And the critical call is at line 4. You can see the library function fcntl for file descriptor control. And the important argument, of course, is the third one. We're saying basically we want to open this up for non-blocking read operations. So that's what does the non-blocking at the API level. Now down in main, that create non-blocking is done at line 5. And again, we have the standard sorts of checks. This being C, we want to make sure every time that we try something, it works successfully. Now let's get into the Epoll part of things. Our application, in this case the Epoller, needs to communicate with the underlying Epoll library, and the communication is bidirectional. We need to send information to the library. We need to get information from the library. To that end, there are two structures, so just collections of fields, and the first I call toKernel because we're going to use this to communicate with the Epoll library, and the Epoll library, of course, is going to make system calls. So in effect, we're talking to the operating system kernel. We're going to get information back from the Epoll library in an array of structures called fromKernel. Basically, for every read event, we're going to have a separate structure, and it's going to contain the information we need in order to read from the pipe. So these two structures are absolutely critical for communicating with the Epoll library. Now, there's some setup. So at line 9, for example, we're basically telling Epoll we're interested only in incoming events. In other words, reads. We're not going to be doing any writing. We're going to be doing only reads. We give the Epoll library the file descriptor of the FIFO so it knows where to listen for activity. And then at line 11, by calling Epoll control, we set all of this up. At this point, we're basically good to go. We've told the Epoll library what we intend to do. We told it where to look for action, and now we're about to use it to detect when there are integers to read. To that end, we go into a while loop, and line 12 is the critical line because it's a blocking call. You see Epoll wait, very nicely named. Basically, we sit here until the library detects some action. When it detects some action, we're leaving out the possibility of an error right now. What it's going to return is the number of events of interest to us, and that's going to be captured in the variable n. So the Epoll wait is the only call we're going to see in this code that is blocking. All the other calls are going to be non-blocking. So when we get some events of interest, we go into a for loop. You can see that down here. And now we do some non-blocking read operations. So the read at line 13, the first argument is where we're reading from. We're reading from some appropriate file descriptor that the Epoll library has given us. So it's basically said, this is the source of the read. We know that. The next line is the address of an integer variable, which is big enough to hold 4 bytes. In effect, we're treating that variable as if it were an array of 4 bytes, and we give the size of that array. So what we're saying in effect in the read is, here's the source, here's where to put the stuff, here's how many bytes we care about, 4. Down here, we check to make sure we got all 4. Now 4 is a sufficiently small number that we really wouldn't expect any problems here. If we were reading, for example, 10,000 bytes at a time, we might expect some problems here, and we might have to have more sophisticated logic. Our interest in this first example, of course, is the API. So this check we would expect to succeed. So if we do get all 4, then we bring the application logic to bear. We check to see if the number is prime. If the number is prime, we update the count. And then we do our cleanup. Basically, both sides clean up, and the named pipe goes away. And then at the very end, there's a short report. This example gives you the look and feel of non-blocking I/O at the library level. Of particular interest is how the application interacts with the library. In this case, the critical part is we do a setup, we wait for the library to inform us of some action, and then we proceed with our non-blocking reads. Let's take a short break. This lesson introduces a second code example in non-blocking I/O. This example is going to be in Java, and for variety, we're going to be using network sockets. In the first example, in C, we saw the Epoll library, which is fairly close to the metal. In this example, you'll see that the Java API is slightly higher level, but the essential challenges are the same. So it won't be hard to imagine how the Java API would translate into, for example, epoll function calls. Let's start then with an overview. So this example uses two separate programs. They're in a client-server architecture. There's a non-blocking client and a non-blocking server, and in the next lesson I'll demo them. The non-blocking client sends HTTP requests to the server after connecting to the server, and then the server sends back HTTP responses. We're interested, of course, in the non-blocking part of all of this, so the server simply echoes the request as its response. There's no tricky application logic here. All of the interesting details are in the non-blocking I/O. The code will make clear that a client request process is actually a two-step. First, the client has to connect successfully to the server, and only then can the client send a request. So on both the client side and on the server side, we're going to see these two distinct steps. All of the relevant data types used in the example, in other words, all of the non-blocking stuff, is in java.nio.channels, a package that was introduced in Java 1.4. So as noted just a moment ago, but emphasized here again, the two programs should be executed separately, and the server should be started first. The client actually is interactive, but if the server isn't running, then the client will fail on its efforts to connect. A final general point should be made. The non-blocking channels used for communication represent an IPC mechanism. In other words, we're dealing here with a form of inter-process communication. So even though the emphasis here is on non-blocking I/O, we're actually back into multiprocessing as well. Let's look now at the server and the client separately, just to get a sense of how they're organized. This will make it easier to get through the many details in the code. So the server begins by opening up a non-blocking server socket channel. The instance of the server socket channel has basically one job, and that's to await client connections. We're going to see yet again a very nice division of labor, a separation of concerns. Every time a client connects, there's a non-blocking read-write channel that is used to exchange request-response. In other words, it's this second channel that carries the communication. And the program needs to distinguish in a while true loop, so the server just listens basically forever for connections and then handles requests once those connections are made. But the code itself needs to distinguish between a connecting operation and a requesting operation. And we'll get into those details when we examine the code. The critical data type in all of this is the Java NIO channels selector. This is basically the monitor, the supervisor. This is the object that sits and waits for connections and requests. It's the library type with which the application interacts in order to determine what's going on. We'll get a very close look at the selector type, and the select method is basically the only blocking call of all of the calls made out of the Java NIO.channels types. On the client side, the client initiates the conversation by opening up a non-blocking read-write channel to the server, and the server, of course, if all goes well, detects that. And the connection occurs inside a loop because the connection call itself does not block. In other words, we can't assume that one try is enough. We may have to wait for the connection to finish. And we'll see that when we examine the code. The client is interactive. It prompts from the standard input for strings to be entered, and those strings are then sent as, in effect, the request, and those strings are then echoed back by the server as the response. The second example, I think, will underscore yet again that whatever the API, the challenges in non-blocking I/O are essentially the same. And the advantages, of course, the gains in efficiency are also the same. In this lesson, we're going to look at the source code for the non-blocking server. The non-blocking server and the non-blocking client are detailed enough that we're going to separate them out into two lessons. So in this lesson, the focus is on the server. In the next lesson, the focus will be on the client. In the Emacs editor, you're looking at the source code for the server, non-blocking server.java. Before we get into the details, let's do a sample run. So let me bring up my bash shell. I'm on a Mac, so I'm going to run the server. And as you can see, a little message is printed out saying that the server is accepting connections on port 9876. Let me now bring up another shell, and I'm now going to run the client. The client is interactive, so we'll feed it some strings. Hello world, of course, to begin. 1, 2, 3, foobar. And you'll notice we're getting echoed responses back from the server. I'm going to quit now. By the way, the order of these responses we'll look at more carefully later. I'm going to quit the client, come back to the server, and the server is reporting the request that it has received and the response that it has sent back. So I'm going to kill this at the command line with Control-C and return to the source code. So the comment at the top goes into the details of compiling and running the two. And what we want to do now is to focus on the non-blocking API at work. Let me jump to line 1 in the source code. You can see the port number set. Basically, the first 4 lines, 1, 2, 3, and then the line below it are setup and logging information. The really important line for us is line 2. You can see that this server socket channel, it's a single job socket, basically. All it does is await connections. It is configured for non-blocking I/O. So basically, the I/O calls that are involved in accepting client connections are going to return immediately. They're not going to block. Line 4 is really important. The Java selector is basically a monitor, a supervisor. We've seen this before in the Epoller example, this sort of construct. So the selector is going to overlook connections and requests. So it's basically got the broad view of what's going on. The next line, 5, is really important. What we do is register the server socket channel with the selector, in particular for client accept operations. So what this line says at a high level is we're interested in accepting client connections. Those connections will be on the server socket channel named server socket. As soon as that's done, we can get to work. So we go into an infinite loop. You kill the program with Control-C from the command line or the equivalent. And the first statement is the only blocking statement with respect to I/O. So you see selector.select. This is basically a wait or a blocking call. So the selector waits until there are client connections. Just for integrity purposes, we make sure that we really have some. So if select returns 0 or less, there's some sort of problem. There's really an error condition. And in that case, we just go back and try it again. Otherwise, we process those connections. You notice the argument to accept connections is selector.selectedKeys. Every connection has an identifier called a key. So the key is just the unique identifier for every client connection. Down here in accept connections, line 9 is the important one. We get the selection key associated with a particular connection. We then immediately remove the key so we don't process it again. That would be a logical error. And there are 2 types of things that the client might be doing, and in fact the client might be doing both of them at once. The first is the client is making a connection. That would be caught by line 11. Key is acceptable. So basically what this says, this is an accepting operation. And then down here at line 16 is readable. This is a client has sent a request that needs to be read operation. So let's take those in turn. If this is an accepting operation, it's the server socket channel that does the accepting. There's division of labor here. But the server socket channel does not actually have read-write streams for communication. In other words, the server socket channel is very specialized. It accepts connections That's it. The socket channel has associated read and write streams so that communication with the client is possible. Once we grab the server socket channel, we use that in the accept call to get the read-write channel. And again, the important thing at line 14 is this. We configure that for non-blocking I/O, and we register this channel with the selector. So we're telling the selector now, for this particular connection, we're interested in read operations. So if the client sends a request, we want to know about it. Now we come down to the read operation. I have a local method called handleRead that does the level details. We'll get to that in a moment. If there's actually something to read, so if the request length sent by the client is greater than 0, then what we're going to do is grab the rewrite channel again, because we're going to use it to echo something back. We're going to create a string called echoing, and then whatever the request was. A byte buffer. We're dealing with networking. Everything is at the byte level. And then we write the buffer back. Now, line 18 is non-blocking. It's also highly optimistic. You'll note that I'm not in a loop, so I'm assuming that everything that needs to be written can be written, in effect, in one fell swoop. On the client side, I'll handle writes in a more sophisticated way for a non-blocking context. But here, I'm being a bit optimistic. Let's jump down to the last piece of this, handleRead. So again, at line 20, it's the socket channel that has the associated input and output streams for reading and writing. So that's the channel that we want. We need to allocate a buffer to grab the bytes that the client's going to send. 1024, 1000 bytes is plenty for this example. And then down here, we do the non-blocking read. Once again, this is non-blocking and optimistic on my part, because I'm assuming that everything of interest to be read can be read in one fell swoop. When we look at the client, we'll handle this in a slightly more sophisticated way for a non-blocking environment. If we got some bytes, then basically what we do is return those bytes from our buffer. We create a string and send that back. And if we didn't get anything, we just send back the default string, no request. The networking here is a bit complicated, but our interest is really in the non-blocking I/O part. So if we go back and sort of scan over the whole program, what we need to do on the server side is basically decide, is this a client who's trying to connect? Is this a client who's trying to send us a request? And handle those two cases appropriately using non-blocking I/O. In this lesson, we turn our attention to the non-blocking client. Last time, we looked at the non-blocking server. In the Emacs editor, you're looking at the source code, non-blockingclient.java. Before we examine it in detail, let's run the client one more time, just as a refresher. I have the server running already, so I launched the client. At this point, the client has connected, so the server has handled the connection event. I'm now going to send a simple request, followed by another request. I now get an echo back from the server of that initial request. I put in one more request. I get the second request echoed, and so forth, until I quit. This terminates the client. And if we go back and look at the server, we can see that the server has been logging, as expected, those requests to the standard output. So let's kill the server now and go back and examine the client in detail. Down at line 1, the first thing the client needs, of course, is the internet address of the server, and that's done in this rather complicated line 1. So we create an instance of an inet socket address. Of more interest to us is line 2, a socket channel. You'll recall that the server had a server socket channel, which is designed to listen for requests. On the client side, all we need is a regular old socket channel that has associated input and output streams, so that basically carries the requests and the responses. The important thing is this: we configure this socket channel to be non-blocking. That's the critical point for us. And then finally, at line 3, we connect. This is going to generate a connecting event on the server side. And as we're going to see, it's going to generate a connecting event on our side as well. Once again, we have a selector, the monitor or supervisor. And what we register with that selector are connection events, read events, and write events. We have a slightly richer context on the client side. Immediately after all of this setup, we're ready to go. And so we go into a while true loop, and basically the selector now takes over. So if there are events of interest, connection events, reading events, writing events, the call to selector.select will return a number greater than 0. This, by the way, again, is the one and only blocking call, the call to select. So if there are events to handle, we call process keys with the selected keys. Recall again that the keys simply identify the events. It's under the hood. We don't care about the details. We don't care what those keys look like. We just need assurance that every event, connection, read, or write, has a unique key to identify it. So process keys gets the relevant keys, and as before, we create an iterator, and then we're going to iterate through this set. So we extract a key and then remove it from the set because we don't want to be processing the same key twice. Now on this side, there are 3 possibilities. We have connecting events, reading events, writing events. Those are at lines 7, 11, and 12, respectively. So let's now look at the connecting event. So the first thing we do is grab the read-write channel, and then notice there's a while loop. So while the connection is still pending, finish the connection. And this may occur, this loop may iterate several times. It depends, of course, on network traffic, network speed, all of that stuff over which we have basically no control. Now, I'm running this, of course, on localhost. That takes a lot of those issues out of play. But in a production environment, the server would obviously be on a different machine. So you see the non-blocking style here. As long as the connection is pending, keep going until it's all done. For read events, I call a local method called getResponse. We'll look at that momentarily. And if it's a write event, I call a local method called sendRequest, and we'll look at that momentarily. So let's start with getResponse. What we're doing here is reading the response that the server has sent back to us. And again, we're in a try block. This is I/O, so bad things can always happen. We grab the read-write channel as usual, allocate a buffer, and now we go into a while loop at line 13. Because the read you see, our channel.read buffer, that returns immediately. That's non-blocking. So what we're not sure of is whether we got everything with a single read. So we basically read until there's nothing more to read. This is a bit more robust than the read we did on the server side. There, we just did one read, and we figured, okay, whatever we get is good enough. Once that's done, of course, we return the response, and then it's going to be printed out. SendRequest is the other side of the coin here. I'm going to use a scanner in order to read input from the user. Once again, we grab the channel and prompt the user to enter a string, and that will be, in effect, the body of the request. So we scan that in. If we get quit, we simply abort. We stop. Of interest to us are lines 17 and 18. So we wrap up the string in a byte buffer. Again, we're doing networking stuff. Bytes are what we're going to send over the wire. And notice now, for the write, we're also in a loop. So while buffer has remaining, read-write channel write. Now this buffer is sufficiently small, so it's 1,000 bytes or so, that almost for sure the write is going to occur in a single iteration of the loop. But we really don't know. If, for example, we were sending millions of bytes, this loop might iterate several times. In fact, almost for certain, it would. Again, this is a more robust and realistic way to do a write because we're in a non-blocking environment. That wraps up our look at the non-blocking socket I/O in Java, that API. And even though the API is fairly high level, the use of while loops and so forth captures the idea that non-blocking I/O is challenging whatever level the API may happen to be. This lesson presents an overview of the polling server, and the polling server rounds out our examples of different approaches to concurrency using web servers as an example. Let's do a quick review. We've already seen the forking server, which uses multiprocessing, and the threading server, which uses multithreading. So the polling server is now the third entry, and it uses non-blocking I/O as its concurrency mechanism. Like the other two servers, the polling server relies on networking code that's isolated in the file utils.c. We don't need to review that code. It's fairly straightforward. What's of interest to us is this. In the standard C library, sockets by default are blocking. So only the polling server sets the sockets to be non-blocking. So that's the distinct difference between it and the other two. All of the code for the polling server, like the code for the other servers, is included in the earlier zip file, and there's a makefile. But let me just underscore again that the epoll library is necessary. So if you're on a Linux platform, you should be able to compile and run without incident, but if you're on a Mac or a Windows platform, you can't use epoll. Let me make a point about performance. None of the three servers is production grade, of course. The multiprocessing server does not have a pool of worker processes. The multi-threading server does not have a pool of worker threads. There are some inherent inefficiencies in those two web servers. But for relatively small requests, if you do some sample benchmarking, what you're going to find is that the performance is roughly the same. And by relatively small requests, I mean requests in the low K range, 2K, 4K, that sort of thing. There are various tools available for benchmarking web servers, and one of the most popular is the Apache AB for Apache Benchmark Tool, and I've provided the URL here if you'd like to take a look. Let's talk a little bit about the division of labor. It's similar in the polling server to what it was in the other two servers, but let's review very quickly. There's a single listening socket. So if this were Java, this would be the server socket or the server socket channel. So that's dedicated to doing one thing, and that's to awaiting client connections. It doesn't perform any read-write operations. When a client does connect, there's a separate read-write socket per client connection, and the server and the client communicate over that read-write socket. What I'd like to do now is to present an overview of the code. I've got a short pseudocode diagram at the top, and then underneath I elaborate on some of the points that I'm going to make. So if you need to come back later and do some review, I'm hoping that the sub-bullets will be helpful there. But I'd like to focus on the main program structure. The thing to notice right away, of course, is that it's complicated. It's more complicated in terms of flow of control than the other two servers, yet again a signal of the challenge presented by non-blocking I/O. So let's start with the outer while loop. This is basically the same in all three. So the web server comes up, it's going to run indefinitely. We're going to kill the web server with Control-C from the command line prompt or the equivalent. The difference now is this. Inside the while loop, there is a nested for loop, and that for loop iterates over all of the pending connection and request events. So again, clients first connect, then they send requests. So the for loop is where all events are managed. An if-else construct then is used to distinguish between connection events and request events. So the connection events are in the if, and the request events are in the else. Now the connection events are a bit tricky. because you could have indefinitely many connections occurring at the same time, and the strategy in this implementation is to handle all of the connections that are pending at once. That's why there's a while loop. The program basically goes through and connects all of the clients that it can at a given time. Then it resumes, and of course, it may then start picking up request events and handling those as well. The flow of control is tricky, again, because the non-blocking I/O forces this trickiness on us. All of the connection calls return immediately. All of the read calls return immediately. Now let me wind up the overview by talking about one simplifying assumption made in the polling server. It's an assumption that we've seen before, by the way, in the Java examples in this section. And that is this: when a read operation is done on a request, my assumption is that I can read all of the bytes in one fell swoop. For robustness, we would have to go into a loop to make sure we got all of the bytes that were sent. In different terms, I'm making the assumption that the incoming requests are fairly small and that the non-blocking read is going to get all of the bytes at once. In a production-grade server, again, we couldn't make that assumption. Furthermore, once the request is read, there's an echo response. So basically, there is a response sent back immediately. It gives the requester, the client, some information about the request, but not much else. So there's no emphasis here in this server, as there was no emphasis in the other servers on application logic. We're interested in focusing exclusively on the APIs. That's the overview of the polling server, and what we'll do in the next lesson is look at the source code. In this lesson, we're going to examine the source code for the polling server. Recall that the polling server, together with the multiprocessing and the multithreading servers, are all included in the zip file together with a makefile. For convenience, the file we're looking at now, polling_server.c, is included in the working files. So let's go to the start of main. Basically, the first four statements are setting up the networking, and the statement of interest to us is the call to create_server_socket with an argument of true. The true means give us a non-blocking listening socket. This socket is going to be used to await client connections. It's not going to be doing the reading and writing. Lines 2 and 3 set up the communication with the Epoller library. So at line 2, you see a single structure named event, and at line 3, an array of event buffers that are used to communicate from Epoller to us. Anytime we want to register an event of interest with the Epoller library, we use the variable on line 2. And anytime the Epoller library wants to give us information about a connecting client or a client that's sending us a request, the library is going to use one of these arrays. So it's a very convenient way for us to communicate with the library. We get a file descriptor that identifies the Epoller library. That's not critical to what we're doing. It's a necessary step, but it's not of particular interest. Now, recall that this variable event is how we communicate with the Epoller library. At line 4, we're telling the library we're interested in incoming events. In this case, that means client connections. We identify the file descriptor that Epoller should monitor for connections, and that's our socket created at line 1. Line 6 is basically the communication with the library. We're telling the library this is what we want, and of course we check to make sure that it's okay. If there's an error message, by the way, there's not much we can do. We're basically out of business. By the time we hit the while true loop then, this is the wait for client connections and handle client request loop. Once we're there, we're in good shape. We've told Epoller what to look for. We're waiting for Epoller to communicate with us. So the critical line is this blocking call at line 7, Epoller wait. Basically, the application sits here until clients connect, or more clients connect, or already connected clients send requests. The variable that is set in this call is going to contain the number of pending events. Should n be less than 0, we have an error condition, we're out of business. Now, the events that Epoller has told us about fall into two categories: connections and requests. The for loop is going to iterate over all of those, and we now have an if-else construct. Let me move the cursor down here to make it a little bit easier to read. The if is at line 8, the else down at line 14. Basically, line 8 is connecting events, line 14 is request events. If the associated file descriptor is the listening socket, that's the if test in effect. Then we go into another infinite loop, and the reason for that is that we could have multiple clients connecting at once, and that represents multiple action on one socket, the listening socket. So we don't know how many there are, we need to handle all of them. So the first thing we do is accept the connection. So this is the library call. We store the return value, which is a read-write socket, in this variable called client. If we've handled all of the clients that need to be handled, we're done. Otherwise, at line 11, we're going to make the read-write socket non-blocking. We're going to be interested in incoming events, request events. This is to simplify the server. We associate the file descriptor with this read-write socket. So in effect, we're telling Epoller, keep an eye on that socket as well for request events. And the Epoller control, again, is how we communicate with the library. Now, for requests, there is no loop because a request would come off a particular read-write socket. The listening socket, by contrast, could have many connections associated with it at once. But a given read-write socket is going to be associated with a particular client only. Now, in the polling server, I make some simplifying assumptions once again. Down here at line 15, I'm assuming that all of the bytes of interest can be read in one fell swoop. The HTTP request is fairly small. If that assumption doesn't hold, then we've got a problem because I will have done here only a partial read. In any case, we check to see that we got some bytes, and if we got some bytes, we echo information about the request back to the client down at line 16. At that point, our business is over, and so we close the associated file descriptor. The close on the file descriptor also tells Epoller there's no need to look anymore at this particular client connection. We're done with it. We've handled the business. This is the end of the program, but the way you would actually kill this program is by doing Control-C from the command line. So we've seen in this example how non-blocking I/O is used in effect as the one and only concurrency mechanism by the polling server, and we've also seen that there's a fair amount of complexity in the code. This is just the nature of the beast. This is the challenge of non-blocking I/O for programmers. This lesson proposes a programming exercise for non-blocking I/O, but also serves as a wrap-up for our focused look at this topic. Let's use the read operation as the representative operation for non-blocking I/O, although the same points could be made with other operations. The whole point of non-blocking I/O, of course, is that the program can handle other tasks instead of waiting for an I/O event to complete. In other words, frees up time that can be put to other uses. And this is evident in a web server such as Node.js. At any point in time, there are concurrent requests and responses that need attending to, and by avoiding blocking, the Node.js web server can jump quickly from one task to the other. So what we'd like to do in a programming exercise is capture this same theme. So what I'd like to do is go back and review the Epoller program. What I have in the rest of this working file, exercise9.txt, are the very points that I'm going to make as we look at the source code. So let me jump to the source code. You'll recall that the Epoller program has two parts to it. There's the FIFO writer, and this is the program that generates a stream of integer values that it sends to a pipe. On the other end, the consumer reads from that pipe. You can see I have the cursor set here to the name of the pipe, pipe 1. This is the FIFO writer.c program. It's already among the working files. It's single-threaded, and it opens up a single pipe, and then it writes to that pipe down in this section of code. It does do some random sleeps to give a little bit of realism to the program. You can see those down here, but the point is there is a single source of data for the consumer program, and that single source of data is basically this pipe. What we'd like to do now is expand that, to have multiple sources. So for example, if you're going to do the exercise in C, I'll have something to say about doing it in Java, or really you could do it in any other programming language that supports non-blocking I/O. But if you're going to do it in C, you could simply have multiple named pipes. And to make the exercise even more interesting, generate multiple threads, each of which would write to a designated pipe. You could also keep it a little bit more simple. You could keep the program as single-threaded and in a loop like this write to multiple pipes. To make it interesting, it would be useful, for example, to write not the same number of values to every single pipe. But the real point here is to have multiple sources of data for the consumer. So let me move now to the Epoller program. So we're now on the consumer side. You can see there's this single pipe once again. There's the epoll setup that we've seen a number of times now. But the key thing is that the Epoller basically reads from a single data source. It does non-blocking reads, but you might say in between the reads, it doesn't have quite enough to do. So the interesting thing would be for it to do a read that doesn't block, another read that doesn't block, another read that doesn't block, where all of those reads are from different data sources. This would be more in the spirit of what makes non-blocking I/O so attractive. Now let me return to the exercise. So basically, I summarize those points down here and make some suggestions about how to do this. The critical point is have the producer, the FIFO writer, write to multiple pipes, and then to have the consumer side, the Epoller, read from those multiple sources and do non-blocking reads. You could do this in Java. Java doesn't have direct support for named pipes, but it does have the file output stream and the file input stream. And for an exercise such as this, these would work quite nicely. In this lesson, we're going to take a fresh look at parallel computing. You're looking at the working file, Parallelism Overview.txt, in my Emacs editor, and there's a line about a third of the way down. Above the line is a summary of what we've done so far with respect to parallel computing, and below the line is where we're going to move to next. So let's do a quick summary of how we've looked at parallel computing so far. We've looked at parallelism as concurrency made efficient. When you're doing concurrent programming, the context is basically this. You have multiple tasks that need to be handled within a given time span, and those tasks are distributed to workers. The workers could be separate processes, they could be threads within a process, they could be some combination thereof. The point is the tasks are distributed to workers, and the workers then need to execute on a processor. So if you have multiple processors, you can have parallel computation. In other words, the tasks can be processed at the same time. This approach to concurrency comes, in a sense, for free, because processes are scheduled by the operating system. If you're doing multi-threading and your API threads map to native threads and you don't have a GIL, there are certain conditions that have to be met, then the operating system also takes over there. So the sort of parallel computing we've seen so far has really been behind the scenes automatic. What we're now going to do is look at parallel computing more explicitly. It's going to come to the forefront. It's not going to be simply an efficient way to do concurrent programming. And there are some obvious reasons why we need to make this shift. For one thing, almost all of the machines that you and I are likely to be using nowadays, including any handheld devices, are multiple processor machines. It's almost impossible to buy a machine nowadays that isn't a multi-core machine, and a core is going to have one or more processors. So how can we best use the opportunity that this hardware support provides us? Now let's dig a little deeper. Traditionally, of course, a processor was a CPU. This was a generic processor, and of course it still is. But in addition, nowadays, you're going to have a GPU, a graphics processing unit, a floating point unit, sometimes called a math coprocessor. You're going to have some special purpose processors as well, and GPUs and FPUs are designed for parallel computing, although in different ways, and we'll get a chance to look at those differences. You may have run across the acronym GPU. It's usually written in lowercase, and it stands for General Purpose Computing on a GPU, and it refers to the fact that GPUs are good for more than just graphics. They were put in machines, of course, to handle graphics, but they also resemble processors designed for so-called supercomputers. So they have an inherently parallel capability. GPUs have come to the forefront in parallel computing as another resource to be used to solve problems in general. Almost all of the machines that we use nowadays are networked, of course. And back in the 90s, there was this famous slogan from Sun that the network was the computer, so you can look at the network as the computer. And what this really means is that software systems tend now to be distributed software systems. They have modules that execute on physically distinct devices. So if you have a network of devices, each of which has multiple processors, you have an incredibly powerful resource for doing parallel computing. So distributed software systems and parallel software systems have intersected. And we'll also look at this approach to parallel computing. Now, there's lots of taxonomies for parallel computing, for parallel systems, parallel architectures. All of this is currently very much in flux. So any taxonomy we may pick today might be obsolete in a year. For example, some parallel architectures emphasize a shared central memory, others emphasize a distributed memory, but in fact, real systems out there tend to be hybrids. The memory models, for example, tend to be heterogeneous, some centralized, some distributed. The key issue, of course, is always how do we write programs that can take advantage of the underlying physical resources, and in this case, how can we write parallel programs? Now, one challenge is that the tool chains, in particular the compilers, still lag behind what's actually available in terms of physical resources. Let me just throw out one example. 2 or 3 years ago, JavaScript published an API for so-called data parallel computing, but there were very few implementations. There were some implementations for development, but there were no widely available distributions. So there's very good hardware infrastructure out there. What needs to happen is that the tool chains have to catch up, and through a series of examples, we'll get a better sense of where the state of affairs is right now. In this lesson, we're going to look at Flynn's taxonomy of parallel architectures. This taxonomy is as old as the hills, but it's still very useful to provide some context. And it's still used quite a bit. It's referenced often in discussions. In particular, the acronym SIMD, pronounced either SIMD or sometimes just spelled out SIMD, that's used quite a bit, and we're going to have some examples of that. So before getting into the details, let me add a couple of cautionary notes. The first is that Flynn's taxonomy is not meant to describe actual computer systems. And in fact, it's not even clear whether a given taxonomy is represented better by a single computer, a network of computers, or whatever. So that issue doesn't really arise. Flynn focuses on two elements in the taxonomy: data and instructions. So the parallelism basically has to do with data level and instruction level parallelism. Let me come down to the abbreviations that I'm going to be using in my very simple depictions of these different architectural choices. D is for data, of course, I is for instructions, and P is short for processor, although Flynn himself preferred the term processing element. In the taxonomy, in acronyms such as SIMD, SISD, and so forth, the S is for single and the M is for multiple. And of course, when we're talking about multiple, we really mean at the implementation level, multiple processors. So let's begin with the simplest choice, SISD. So this would be read single instruction, single data. And here's a very simple depiction of it. This represents, if you like, the base case. There's no parallelism at the data level. There's no parallelism at the instruction level. So this is realized by an old-fashioned single CPU machine. Although that's not our emphasis. We're not trying to classify existing machines. SIMD is of particular interest to us. The first couple of examples that we're going to see will focus on this. And this, of course, is single instruction, multiple data. Various programming languages have support. And there's lots of interest in this in modern computing, with large data sets and so forth, but we'll get into the details when we see some code examples. And here's the depiction: 3 data sources, 3 processors, and a single instruction source. If you want to think of an example, think of an array that has elements, and think of all of those elements as being different data values. So there you have multiple data items, if you like. And think of an instruction that's going to compute the square root of each. Suppose the values are all non-negative integers. You could do that obviously in parallel because there's no dependency among these multiple data items. MISD is, of course, multiple instruction, single data. Some have suggested that you could look at fault-tolerant systems this way. I don't want to spend too much time debating that point, but here's a simple depiction of this. There's a single data source, so the same data items flow into the processors, but the instruction sources are different. So you have separate instruction streams, if you like, but a single data stream. And then MIMD, parallelism now in both the instruction level and the data level. So this is multiple instruction, multiple data. It's been suggested that this captures modern distributed systems. We're using this taxonomy really for context, for reference. And here's a simple depiction. So we have 3 processors, 3 data sources, and 3 separate instruction sources as well. If all of these processors are working on the same problem, then there needs to be communication among them in order to, for example, aggregate results. This, in any case, is Flynn's very famous taxonomy. It's been widely debated, widely discussed, it's been amended, there have been additions and so forth. But for our purposes, it's a good starting point, and it's particularly important to get the SIMD out on the table. In this lesson, we're going to look at 2 C programs. The first has no data parallelism, and the second does. You're looking at the source code for the first. The file is called non-simd.c. The SIMD, of course, comes from Flynn's taxonomy, single instruction, multiple data. And I'm going to use that acronym interchangeably with the term data parallelism. Let's get to the code. As you can see, I have 2 small arrays. Array 1 is initialized to 8 values, 1 through 8 ascending. Array 2 is initialized to 8 values, 8 through 1 descending. And then there's a sum array, which is uninitialized, because in a for loop, I'm going to sum the elements in the array 1 and array 2 and store those values in the sum. And then for good measure, I print this out. Now, this is an old-fashioned serial program, non-parallel program, and there's obviously a better way if we had a compiler and hardware that would support it. The better way would be to sum 8 and 1 at the same time we're summing 2 and 7, at the same time we're summing 3 and 6, and so forth. This, in other words, would be an ideal case for data parallelism. As it turns out, I have a machine with an AMD processor, so any Intel-compliant processor would be good enough. And this processor supports what in Intel speak is called SSE, Streaming SIMD Extensions. And what that comes down to is new instructions, a smaller instruction set added on to the current Intel instruction set, in addition to some extra CPU registers. If you'd like a longer take on this, I provided documentation at the bottom of the program. What I'd like to do is jump to the second program to show how we can use this. So we're now looking at the source code simd.c, the program that does data parallelism. The thing I'd like to emphasize is at the top, I compile this in the usual way, and then executing as usual. I do need to explain one thing, because there is some special code in here that's a heads up to the compiler. So for those of you who haven't used C, let me review the typedef. You see an example here, typedef unsigned Boolean. What this does in C is it makes Boolean an alias for unsigned. In other words, any place where I could use unsigned, and that's short for unsigned int in C, it's a 32-bit unsigned int. Any place I could use unsigned, I could now instead use Boolean. Let me come down to the typedef that's of interest to us and to the compiler. So you see the typedef here. The already existing type is int, that's a 32-bit signed integer in C, and my alias is int v8. The v is for vector, the 8 is for the number of ints in the vector. The all-important addition is this underscore underscore attribute underscore underscore. This is a heads up to the compiler, and what I'm telling the compiler in particular is this: int v8 is a vector data type. In other words, it's really an array, and what I need for an int v8 is length, that's 8, times size of int, which is almost for sure 4 on any modern computer. So I'm telling the compiler, in effect, I need 32 bytes. Now with that done, we get some very nice features. I declare two variables, data type v1 and data type v2 of type int v8. Notice, by the way, there are no square brackets. So data v1 and data v2 don't really look like arrays, but I'm able to initialize them as if they were arrays. So you can see the initializations here. Then, for good measure, I add the two vectors. Notice there's no looping, there's no array syntax. I multiply the two vectors, I divide the two vectors, and then for good measure, I print out the sum vector, the addition vector. The only place you see any array syntax is in this for loop. You see the square brackets, add square brackets I. So this is typical array syntax in C and in most other modern languages. But above this line, the for loop line, you don't see any array syntax whatsoever, although the initializations do look a little bit weird. So what I get from this code is data parallelism with very little effort. I compile it in the usual way, and as I'll show you, I run it in the usual way. So here's the non-parallel version. It's exactly what we'd expect. So I'm in my bash shell prompt. Here's the parallel version, and we would expect, of course, to get the same result. Later on, we will see a case where there will be significant performance boosting. For now, we're interested in the idea of doing data parallel programming with as little effort as possible and this is about as good as it gets. In this lesson, we're going to get very close to the metal. We're going to look at some assembly language code for the SIMDC program that we saw last time. In my Emacs editor is the source code SIMDC. The code creates two data vectors and initializes them. That's these two lines, data v1 and data v2. And with that in place, we're now able to do parallel addition, parallel multiplication, and parallel division. Notice there's no looping. There's no hint here that we're dealing with vectors rather than with scalar values. So the syntax is clear, it's straightforward, it's easy on the programmer. What we want to do now is get a look at how this really happens. In other words, how it happens at the machine instruction level. I'm going to introduce a new file. This is called simd-doc for documented.s. And let me talk about how I got this file. The way C is compiled is as follows. It actually goes through a four-stage process. The source code goes into what's called the preprocessor. That handles anything that starts with a sharp sign. Sharp sign include, sharp sign define. The output of the preprocessor goes into the C compiler, which generates assembly language code. That assembly language code goes into the assembler, which is the assembly language compiler. That generates so-called object code, binary, that's machine instructions. That code goes to the linker. The linker needs to connect the compiled program with whatever libraries are necessary to make it run, for example, input-output libraries. And the end result is executable machine code. Now, when you compile in C, you can stop the process any place. If you look at this command, gcc -S sim.c, that will produce by default the file simd.s, which is the corresponding assembly language code. Both GNU and Clang could be used to compile assembly language code directly. The assembly language, if you've not seen it before, can be a bit forbidding, particularly on an Intel machine. I've got some bullet points explaining some syntax, but I've also got a little depiction. So one of the instructions we're going to see is this, move L. That's really copy L. L stands for long word. A long word is 32 bits, 4 bytes. So what this command says is copy $1. $sign means literal, so copy 1 into this location. And this address is a bit tricky, so let me explain it here, and then we'll look at the picture. %RSP is a register that acts as a pointer. RSP stands for Register Stack Pointer, and the 96 is an offset. So the address is actually $RSP plus 96. In an Intel architecture, the stack grows from high addresses to low addresses. So at some point, the stack pointer, RSP, points at some location on the stack. The displacement, RSP plus 96, is at a higher address, and the move instruction puts 1 into that address. The selection of these addresses was made by the compiler, and it made all of the decisions. We're just trying to understand those decisions. Now let me move into the code. So the top part of this assembly consists of move this, move that, move the other thing. These are all constants. 1, 2, 3, 4, 5, 6, 7, 8. That's the first vector. 8, 7, 6, 5, and so on. That's the second vector. 1 goes into the position 96 above the stack pointer. The next at 100. The next at 104. The offsets increase by 4 bytes. The data vector 1 starts here and ends here. Data vector 2 starts here and ends here. All of the data values in the two vectors have been stored onto the stack. We have some tricky little instructions here, but this is really the key to what we're interested in. Anything beginning with a percentage sign, by the way, is a register. If you look here at the register, you see XMM1. and down below XMM0, XMM2. Altogether, there are 16 of these XMM registers. Those registers are 128 bits in size. This statement, move DQA, the DQ stands for double quad word. A quad word in Intel is 64 bits, so a double quad word is 128 bits. Basically, this says, go to this address where 1 is stored and take 128 bits and put them in here. So effectively, what you have is half of data vector v1. Recall that the data vectors hold 8 integers apiece for a total of 256 bits. So the whole vector won't fit in a register, half of it will. That's the key. This instruction basically does the same thing for data vector 2. It puts half of it in the register XMM0. Which registers are used is not really important. This instruction now does the add. So you see P, the P is for pad, add, and this is adding 32-bit quantities. The register XMM1 is one of the sources, but it's also the destination. XMM1 equals XMM1 plus XMM0. So in effect, we've now got the sum of half of the two vectors. Finally, down here on the second add, we get the sum of the other half. So at this point, we have added data vector v1 and data vector v2. The code now does the following. It takes the contents of this register and it stores it back to the stack, and then it does the same for the other half, stores it back to the stack. These same registers are now going to be used in the multiplications and the divisions. So the trick, what the system is doing in effect is this. It's saying, let's take the data vectors in the source code. We'll store those values in memory, in particular on the stack. We'll then move the values into these special registers, the XMM registers. We'll do the special parallel add. As I said, the P stands for padded, but it's a parallel add. With two adds, we can add together all of the elements in both of the vectors and get the sums. Now let's take those sums and move them back to the stack because we need to do some multiplication and then some division. The Intel assembly has gotten better over the years. We're looking here at a 64-bit version. Depending on which Intel family processor you may have an AMD, you may have an Intel, which version, which compiler you're using, GNU or Clang, you may get slightly different results. But for example, the C program that we looked at, I compiled on both a Linux box and on a Mac, and it ran just fine in parallel, although the assembly code is slightly different. In this lesson, we're going to focus on how data parallelism can boost performance. We're going to look at a program that uses what are called the SSE, so the streaming SIMD extensions, the SSE intrinsics, which is a library that Intel provides for doing this sort of programming. The key header file is the second one here, xmnintrin.h. And we'll get a look at the code shortly. The working file you're looking at is ssetimings.c. This should work on any platform as long as the underlying processor is Intel compatible and if the compiler is either GNU or Clang. Let me explain what's going to happen. I'm going to create some vectors of roughly 2,000 in length, so you can see it's 2048. I want to stick with powers of 2. And I'm going to populate those vectors with floating point values this time instead of with integer values. You see I have the value 4, so let me explain what's going on. Down here you can see the vectors v1, v2, v3, r1, and r2. r1 and r2 are the result vectors. And you'll notice there is a special attribute, and you see aligned 16. 16 refers to bytes. So basically, what we're telling the compiler is that when you lay out these vectors, you've got to make sure that everything is aligned on a 16-byte boundary. 16 represents 4 ints or 4 floats, because on modern hardware, a typical int, certainly a C int or a C float, is going to be 4 bytes in size. So the vectors are laid out deliberately so that one of these vectors, 16 bytes of which, will fit nicely into one of these XMM registers. Now, the init function here is of no particular interest to us. It just initializes each of the vectors with relatively small floating point values, but that detail is not so important. And then I have two functions. One is called inSerial. It's a pretty good indication of what's going on. You can see a for loop, and the result vector 1 is computed as follows. It equals vector 1i plus vector 2i times vector 3i. The in parallel code is down here, and it's a little complicated because these extensions come in. What we're doing here is creating pointers of a special type, __M128. This is suitable for taking things from the stack and putting them in registers. So there's a little bit of setup in the first 4 statements. We come down here and set n. So n is the length, 2048, divided by aligned vals, that's 4. We're now down to 512. In the serial version, what we're going to do is iterate roughly 2,000 times. In this case, we're going to iterate roughly 500 times, so about 1/4 the number of times. And that's because we're going to be using these special instructions, one for multiplication and one for addition, that are basically going to work on 16-byte chunks at a time. So we're going parallel. This is a little timing function. It's recommended in the Intel's developer guide. It contains some inline assembly. The timeIt function basically takes the start time, the stop time, and then computes the elapsed time. And we'll do a run. You'll see how that works in just a moment. So what the program then does, in effect, is it runs the program, the serial function first, then it runs the parallel function second, and we get the times. So let's go to the command line, my bash shell. Let's do a sample run. I've already compiled. By the way, the compilation is straightforward, no special flags or anything. Let me do it again because you'll see the numbers don't come out exactly the same. Timing is a very difficult business. But you can see the parallel version takes roughly half the amount of time as the non-parallel version. So there is a boost in performance. Now, the downside, of course, is that the code is not the prettiest stuff that we're ever going to look at. But the important thing is that it is far more efficient than the serial version of the code. In this lesson, we're going to take our first look at OpenMP, which is a library, a set of tools, and an API for doing what people sometimes call auto-vectorization. This basically is data-level parallelism, and I have on the first line of the working file, OpenMP Overview.txt, the URL for OpenMP. In order to get a better sense of what OpenMP does, let's look at what we've been doing so far. So we've had 2 SSE examples in C, and these examples illustrate what can be called instruction set level data parallelism. And let me recall, just for quick review, the first example. So in the first example, I had to do very little. I did have to create this typedef with the attribute defining a vector size. So basically, I was telling the compiler, I'm going to have vectors that contain 8 integers. Once that was done, and I had initialized the vectors, I could do add, multiply, and divide just by using the standard operators on the vector identifiers. It's really the compiler that did the heavy lifting, and that, of course, is a good thing. What the compiler did was take advantage of extensions to the Intel instruction set. So they're new instructions added to the Intel instruction set for SSE. These instructions, in turn, take advantage of new hardware support, in particular these 128-bit registers with names that begin with XMM. Now, under the hood, we saw in the assembly code these new instructions. They included, for example, this PADDD for padded add of a 32-bit value. It's the compiler that generated those instructions, put them together in the right order, and so forth. All of the work was really done at the compilation level. In the second example, we used the SSE extension API, and there were some funky library functions in there. You'll recall there was one called _mm_mul_ps. But those library functions generated sequences of machine-level instructions that did what we wanted them to do. And what we wanted them to do was data parallelism. So this was the example where we did the timings. There was no multiprocessing and no multithreading anyplace in those two examples. And that's what I mean by instruction set level data parallelism. We relied on particular instructions that were able to do the data parallelism. With OpenMP, we're going to take a different approach. We're going to use multithreading for auto-vectorization, or data-level parallelism. Now, OpenMP is a spec. It's really multithreading. The specification is for thread-based parallel computing with shared memory. So the assumption is that all of the threads have access to the same memory location. There's support for various compilers, but the best support is for the GNU compiler. The support for the Clang compiler that comes with a Mac is not quite so good. You'd have to do a little bit of a setup. My recommendation is to install GNU on a Mac if you want to run these examples on a Mac. If you're on a Linux box, a Windows box, and you have the GNU compiler already, you should be good to go because OpenMP support is built in. But for a Mac, it isn't. The examples I'm going to run are going to use the GNU compiler on my Mac. Now, OpenMP can be used for concurrency. In other words, the sort of parallelism that we've been emphasizing up to the most recent lessons. But really, it's designed for auto-vectorization or data-level parallelism in general. And we're going to see examples of both stripes, but we're really going to emphasize the data parallelism. OpenMP is high-level and very powerful. Later on, we're going to look at something called MPI, which is the message passing interface, and there is something known as OpenMPI. We'll hold off on getting into the differences until we finally see MPI. This lesson covers our first code example using OpenMP. You're looking at the file basicomp.c. It's the source file in my Emacs editor, and the cursor is right to the left of the compilation command, so that changes a little bit. I'm using a GNU compiler on a Mac just because it has better support for OpenMP, and the command is gcc -f OpenMP, then the name of the file, and then the desired name of the output file. Once it's compiled, the code is run in the usual way, and of course we'll do a sample run in a bit. For now, I want to describe what the source code looks like and how it behaves. So there's a new include. This is at line 1. You see omp.h. That's the so-called header file. It's basically the interface. It describes all of the functions that are in the OpenMP library for C and affects C++ as well. At line 2, inside main, I declare two local variables. T_count is going to be the thread count. I initialize that explicitly to 0 for emphasis. And TID is going to be a thread identifier. Now we get to the critical part, line 3. So we've not seen this sort of thing before in the C examples. So you see # pragma. This is basically a directive aimed at the compiler. So we're telling the compiler, in effect, we're using OMP, we basically want parallelism on the block that follows. So let me describe the block. In C, a block opens with a left brace and closes with a right brace. We're telling OpenMP we want this region of the code to be multi-threaded. Now there's some more information at the end. Variables in an OpenMP application can be shared across the threads or private to a particular thread. We're telling OpenMP we want key count back there from line 2 and TID also from line 2. We want each thread to get its own copy. So that's what private means in this context. So there's going to be automatic multi-threading of this block. What the block does then is it calls a library function, OMP get thread num, store that in the TID variable, print it out. So we're going to identify each thread. The so-called master or main thread has an ID of 0. The master thread only is going to print out the total number of threads. Now, at the close of the block in OpenMP, there's an implicit wait. In other words, this putS statement at the end, goodbye cruel world, is not going to execute until all of the threads are done executing this block. So you might say, we get with OpenMP automatic multi-threading and automatic waiting. So let me now run this, and I can clarify the code a bit more. I've already compiled it. I'm going to do a run from my bash shell. And you can see the threads there in the output 1, 2, 3, 4, 5, 6, 0, 7. That's a little bit unusual. I'll run it again so you can see. Again, let me do yet another one. This time there's a little difference. Thread 5 does its output first, then 1, then 2, and so on. The second to last line of output is the thread count on this machine is 8. So what OpenMP does by default is it takes the number of processors on the machine, and then it generates that as the number of default threads to execute this block. As you'd expect, we can also tell OpenMP how many threads we want. But by default, it's going to pick the number of threads to be the number of processors available on the host system. Now, this particular example illustrates the API, talks about the control structures, but it doesn't really do any data parallelism. For now, the idea is to become more familiar with the OpenMP API. In this lesson, we're going to look at the Miser-Spendthrift problem. There are 3 short programs. The one you're looking at in my Emacs editor, msomp1.c, doesn't use any OpenMP at all. It serves as the base case. It's there for contrast with the other 2. Because this is the Miser-Spendthrift problem, the emphasis again is on concurrency, not parallelism, and we're interested in OpenMP mostly for parallelism. But concurrency, trying to manage threads and so forth, should shed some light on how OpenMP works. So let me lay it out very quickly, the first program. There's not a whole lot to it. Once again, we have the bank balance. It's initialized to 0. There's a for loop that iterates 8 million times. It's a tight loop. The balance is incremented and then decremented. There's no multi-threading, hence there's no race condition. The balance is going to wind up as 0 at the end. Now let's switch gears and go to the OpenMP version that induces a race condition. So this is badly written, deliberately so. We've got the balance initialized to 0. We're going to iterate again 8 million times. Now let's look a little bit more closely at this pragma. All of the OpenMP commands for the compiler, technically these are called directives, begin with sharp sign pragma. That's part of C. Next comes OMP, and then there's various pieces of information. We're telling OMP that we'd like to go parallel, and this, of course, is thread-based parallelism, and we'd like to do it for the body of the for loop. We're telling OMP to multi-thread the entire for loop. Now, some things we don't have to tell it. For example, each of the threads is going to get its own copy of I. the balance is going to be incremented and decremented by each thread. The balance is a static in order to underscore that there is exactly one copy of it. At the end of the for loop, this is the end of the parallel section of code, and the OMP compiler is going to put in a wait there. In other words, the multi-threading is going to occur from here to here. Then there's going to be a wait until all of the threads have terminated, and then we go back into single-threaded mode and we print out the balance. The number of threads in this example is not specified, and so it defaults to the number of processors on the machine. I have 8 processors, so we're going to have 8 threads in action. And in the earlier examples, we've seen printouts of that. So this is the race condition version. Now let's look at the fix, the third version, MSOMP3.c. Now we are going to make sure that there isn't a race condition despite the multi-threading. The pragma at line 1 is exactly the same as before, but now we have 2 nested pragmas, pragma OMP and now atomic. So basically we're saying that we want the following statement to be locked. And that, of course, is the balance equals balance plus 1. And then we do the same for the decrement operation, balance equals balance minus 1. We could, by the way, lock more than a single statement. We could lock a block, but for emphasis in this case, we're locking a single statement, and there is one lock for both cases. A given thread can do this, a given thread can do that, but you'll never have simultaneous execution of this and that. So we get exactly the behavior that we want. When we run this, you're going to see that there is a noticeable slowdown because there is a cost to thread synchronization, to locking. Let's go to the command line prompt. This is my bash shell. Let's run the first version. And the second version, we'll run it a couple of times just to show that there is a race condition. We haven't gotten a negative value yet, but if we go long enough, we should. And now let me run the third version, and you'll notice the pause. This is going to take some time, but the balance is going to be 0. So the second version is the race condition. This version is going to be the locked version. And we'll do it one more time for good measure. And you get a sense of the cost of thread coordination. In the next lesson, we'll return to putting OMP back to its intended use, and that is in support of parallelism. In this lesson, we're going to focus on 2 examples that use OpenMP for data parallel programming. We're going to study the auto-vectorization capabilities of OpenMP. Let's bring it down to earth by looking at the first of the 2 code examples. And the documentation provides a very quick overview. So what the program does is a familiar data exercise. It converts Fahrenheit temperatures into centigrade, and it does n at a time. In other words, it does these in parallel. N is the number of processors on the host system. I'm running this on a MacBook Pro, so in this case, n is 8. The working file is called temp.conv.c, so it's the source code. Let's get into the code. Here's the include for the OMP library. This is the interface, in effect. The random number generator here is used to generate values between 0 and 99.9. The code is a little bit obscure. I'm trying to get reasonably good random values, so the details are not so important to us. F to C does the conversion. It takes in a double, and then it does the conversion, prints out the result. So let's cut now to the core of the program. There's a pragma, a block, and a very, very simple call in that block. Pragma OMP parallel. So we're just telling OMP to execute everything in the block in parallel. F to C is going to be executed, in this case, 8 times in parallel. There's an implicit wait at the end of the block. So basically, we wait until all of the threads have done their thing, and then we're going to return to single-threaded mode and the put s is going to send out a greeting, and then the program is going to terminate. I've included output from a sample run below, but I'll run the program right now. So let me go to the command line prompt, bring up my bash shell, and let me do a temp convert once, and for good measure, let me do a second one. And you can see the temperatures are converted straightforwardly, and we actually got the same number both times for the first temperature. Let me now clear the screen because we're going to look at a second example and then run that as well. So I'm going to go back to my Emacs editor and now bring up a richer example, one that shows off the real power of OpenMP. We're now looking at a file called divideandconquer.c, and this is a bit more complicated. I've summarized what the program does in the documentation, but let me do that by turning to the source code. So what I have here at line 1 is job size defined to be 100. Basically, I'm going to have 3 vectors, each of which is going to hold 100 data items. They're going to be floating point values. And then I've got a chunk size of 10 at line 2. So what I'm going to do is ask OMP to break this job up into chunks and basically allocate each chunk to a separate worker thread. OMP is going to do this automatically and very nicely. So I have some local variables here, thread count, thread ID, I, and the variable chunk set to chunk size. Chunk size in technical terms is a macro. It's not a variable, so the preprocessor will get rid of that. It's important that I have a variable that has that same value. I now go into a simple initialization loop. All I'm doing is taking vectors A and B and populating them with values. And now we get down to the heart of the program, the pragma OMP. Parallel, we're telling it do the block below in parallel. The shared variables are going to be vectors A, B, and C, thread count, and chunk. And then the private ones are going to be I and TID. The private ones are individual copies per thread. So I think this is fairly intuitive. Here we get the thread ID for each executing thread, and if it happens to be the master thread, the one with ID 0, we print out the thread count. And then for all threads, we print out a little message just saying that this particular thread has gotten some work to do, and that work is going to consist of a chunk. Line 6 is the part that I really like. You see pragma OMP 4. So this covers the for loop. And we're telling OMP we wanted to do dynamic scheduling on chunks. So if you look at the for loop at line 7, notice that it goes from 0 to less than job size. Job size is 100, but basically OMP is going to chunk this up into jobs of 10 apiece, and it's going to do all of the bookkeeping. And as you might expect, it's just a standard vector operation. We're going to take elements in A and B, add them together, and store them in C. So nothing very exciting there. But this is really powerful. We're dividing the work, and then OMP is going to ensure all of the work gets done in the recommended chunk size. This, again, is the implicit wait, because it's the end of the block that we've asked OpenMP to parallelize. And then there's a little message that we're back in single-threaded mode. And for good measure, I'm going to print out the result vector, which is basically sums. Let's see this guy in operation. So this is divide and conquer. What I'm going to do is pipe this through more from the bash shell so we can get a look at the output. We start out, worker 5 is getting some work, worker 7 is getting some work. Then you see an empty line followed by thread count 8. It's the master thread that's printing that out. So 5 started, then 7, then thread 0 started. Then 1's getting some work, 4's getting some work, and so on. You see which job which thread is doing. So for example, if you come down and look at the first of these with a capital W, you see worker thread 5 has done C0 equals, and then worker thread 7 has done C10, and so on. All of the chunking is being done, and if you now come to the very end, you're going to see that everything in the array has been done. We don't know quite the order in which it was done. We don't care. What we care about is that the job was done in parallel, it was properly chunked, and that OMP did all of the tedious bookkeeping for us. A very, very nice API, I think. Reasonably clean code. If you think about doing this, for example, in Java or in C yourself, straightforwardly, there's obviously a bit more work. Although Java does now have the fork join framework, which is very similar in spirit to the sort of thing we're seeing here. In this lesson, we're going to take a look back at the various programming examples that we just went through. So let me start with a high-level overview. We saw data parallelism, sometimes called auto-vectorization, SIMD or SIMD parallelism, basically at two levels. The instruction level, there was no multithreading, no multiprocessing. And the second category consisted of multithreading. So there was data parallelism. It consisted of threads doing work in parallel. Let me start with the first category, the instruction level parallelism. There were two examples. The first was the SIMD program, and I summarize it here in the working file wrapUp10.txt, but let's go back and look at the source code. We looked at both the C and the assembly language code to see what was really going on. I'm going to stick just with the C. So here's the short version. As programmers, we had to do a type def that described a vector. In particular, we had to tell the compiler how many bytes we needed per vector. So our vector consisted of 8 integers, and on a modern system, an int is going to be 4 bytes, so we needed 32 bytes per vector. Once the compiler was given that information, life became pretty easy. We could declare and initialize a couple of vectors. There's not even array syntax used here. And then we could just do add, multiply, and divide very, very easily at a high level. Nothing more was required. In the second example, we did a little bit more work. We basically used some library functions that the compiler translated into parallel instructions. This was the SSE timings example. Let me bring that up. So as you'll recall, we had two functions, one called inSerial, the other called inParallel, and we did timings. Here's the big picture. In inSerial, the loop iterated about 2,000 times. In inParallel, it iterated about 500 times, so about 25% of the times. There was some setup required. We had to declare these pointer variables of type __M128. Basically, we were telling the compiler that the vectors we were using were suitable for storing in these special CPU registers, the XMM registers, in effect. Down here in the for loop, we used special library functions, _mm_multiply, _mm_add. And what that allowed us to do, again, was to cut down the number of iterations from 2,000 to about 500, and we got a significant boost in performance. We'll come back to that topic in a later lesson. For now, let me go back to the summary document. The last example that we saw was the divide and conquer example, and this for sure was the richest. It really highlighted the power that OpenMP provides. So I'd like to bring that code up, and all of these working files are available. So let's recall how this worked. We have two pragmas for OMP, top level one, and it tells OMP that we want the following block from here down to here to be multi-threaded. Since my machine has 8 processors, OMP by default is going to create 8 threads to do the work. And then down here, we tell OMP that what we want it to do is dynamic scheduling. In particular, we want it to take the job, which consists of vectors of 100 values, and we want it to break it up into chunks of 10. So the loop looks as though we're going from 0 through 99, job size is set to 100, and doing these vector additions. But in effect, the OMP is dividing that labor up among the threads. Each thread is doing a chunk of the work. A chunk in this example happened to be 10. And OMP is also ensuring that all of the work done on the chunks is properly aggregated. At the end, we get exactly what we wanted to get. So let me go back to the wrap-up document. What I've done by pointing to the examples is summarized in this document, and I hope that this overview of what we did proves useful. In this lesson, we're going to focus on the connection between parallelism and performance, in particular how parallel execution can boost performance. I'm going to rely on code examples, in particular a revision of the SSE timings program, and we're also going to take a look at a fresh Java example. Let me go back to the SSE timings program. This program involves vector operations. We did them first in serial, then in parallel, and compared the timings. In the original version, the vector sizes were 2048. So roughly 2K. What I've done is revised the program in 3 ways. I've now got a 2048 version, that's the original version, an 8192 version, I increased the vector size 4-fold, and then a 32768 version, which increases 8192 4-fold. So I'm going to run the programs at the command line shortly, but earlier I did a bunch of sample runs, 20 for each, and then averaged the results, and here's what I came up with. The timings 2048, the in parallel execution was roughly twice as good as the in serial. For 8192, that number dropped a bit to 1.72, and in the last version, for the biggest vector size, the average speedup dropped. Now, this is not a rigorous test, but it raises some interesting questions, in particular, what could be happening here to account for these numbers. And these numbers are going to differ depending on the platform you're on, and even on the same platform on the runs that you happen to go through. So let me do the runs. Here's the 2048 version. So you can see here I did slightly better than my earlier average, 2.23 speed up. And now let me do the 8192. And you can see this came down a little bit, 1.87. Just to recall the number, it's 32768. So let me run that version. And you can see this dropped off down to a speed up of 1.42. And you see the timings for the various runs, the in serial and the in parallel. So the trend is the same in these runs as with my earlier data, although the numbers differ slightly. Now let me return to this working file, performance.txt. We're looking at it in the Emacs editor. If you go back to the in parallel versus in serial functions, the difference is this. In the in parallel function, we iterate through the loop only 1/4 the number of times. And this is because we're taking advantage of those special Intel instructions, in this case in the form of library functions, and we're taking advantage of these special 128-bit registers. The loop is reduced by 3/4 for the in parallel version, and each time in the loop, what we're doing in effect is we're handling 4 floating point adds and 4 floating point multiplies at a time. So that's where the savings comes in. If you look at the numbers, however, the biggest speed up we get is over 2. It's not even at 3, not even close to 4. So the obvious question is, why don't we get a better boost in performance? And this is one of the questions that's going to motivate our technical analysis. To begin, however, we need a little bit of background. We need to talk about how best to measure performance. So there are basically 2 sound measures. One is response time. It goes by different names, sometimes response time, sometimes latency, but the idea is pretty intuitive. You start a program, click the stopwatch, When the program terminates, click the stopwatch again and see what the elapsed time is. So for example, if program P1 takes 10 time units and program P2 takes 5, then if you look at the ratio, P1 over P2, there's a speed up of 2. So response time is very straightforward. Slightly trickier is throughput, the number of tasks or jobs completed in a fixed amount of time. I've got some verbiage, but let's go to the simple depiction of this. I'm on a single processor machine. I have task T1 that takes 3 time units. Task T2 takes 5 time units. So it takes 8 time units on machine 1 to finish both of these tasks. So the throughput is basically 2 tasks and 8 time units. What the time units are, we don't care. Seconds, milliseconds, nanoseconds, that's irrelevant. We just have to keep that fixed. Now we move over to a multiple processor machine M2. We run or process the same 2 tasks. T1 now goes up from 3 to 5, so notice its response time has increased. The response time is less efficient. T2 still takes 5 time units. There could be differences between the machines. One machine is good at floating point, the other is good at integer operations. So there are all sorts of reasons that could account for this difference. All we care about is that in 5 time units, we are completing the 2 tasks. So we've increased throughput, and this represents a speed up of about 1.6. So the big picture that we want to take away from this example is the following. Parallelism, which increases throughput, is a good way to boost performance. In this lesson, we're going to look at a Java code example that highlights the relationship between parallelism and performance. In my Emacs editor, you're looking at the source code, ParallelSort.java, and this code uses features that were introduced in Core Java 8. To compile and run, you're going to need Core Java 8 or greater. And in the documentation at the top, I've got a short explanation of what the program does. But let's jump right into the source code. So as a field, I have an integer array to sort, and then down here at line 1, I set the array size to 4 million and change. I'm trying to ensure that we have a power of 2. That's why you see 1024 times 1024 times 4. We call init to initialize the array, and then we call sort array. The first argument, of course, is the array to sort. The second argument is false. The false in this case means don't do the sort in parallel, do it the old-fashioned way in serial. So we capture the elapsed time, the response time. We reinitialize the array because the array is now sorted, and then call sort array a second time with a second argument of true, and that means, of course, do the parallel sort. Then there's a little report at the end. What I'd like to do is jump to my bash shell and run the program for you. So I've compiled it already. It compiles in the usual way with Java 8. It's going to pause a little bit. This is a big array to sort. The elapsed time in serial is 400. That happens to be milliseconds. We don't really care as long as it's the same unit used in each case. And then in parallel, it drops down to 137, so we have a speed up of almost 3. Let's do it maybe one more time. Here the speed up is 2.8, maybe one last time. Roughly the same sort of speed up, above 2.5, below 3.0. Significant speed up in any case. Now let's return to the source code and look at the features in Java that do this. So I want to come down here to the init. So all the init does, as you can see, is creates an array. And then it uses some new Java 8 features. In particular, you'll notice at line 4, there's now a static method in the java.util.arrays class called ParallelSetAll. So the first argument is the array, and the second argument uses the new lambda expression syntax in Java. What this does, in effect, is it sets each element of the array to a randomly generated integer value. So the I is a local variable. It is the index into the array. so the parallel set all understands how this works. What this does is initializes all elements in parallel rather than doing them in serial. So this is an under-the-hood time savings. The main point of interest, however, is the sort array. You can see here we capture the start time, and if the parallel flag is set, we do the parallel sort. If you look at the documentation, you'll see that this uses a version of merge sort. This sort is more efficient than the old-fashioned way, which is a quicksort, and in fact a variant on quicksort called dual pivot quicksort, which is still a very good sort, but for a large array of 4 million and change, the parallel sort clearly won. We got a significant speed up in performance. The rest of the code just has utility functions for printing out the results and so forth. We want to now get more technical about figuring out how much boost we should expect and how can we analyze the boost that we got. The goal of this lesson is to gain a sharper understanding of how performance and parallelism are related. The way we're going to do that is by taking a quick look at Amdahl's law, and the working file that you're looking at in my Emacs editor is just called amdahl.txt. I have a bunch of notes to guide us through the discussion, and I've got an example with numbered steps down below. We'll get to that in a moment. So a very quick word on Amdahl. He's a one-time IBM engineer who went off and started his own company that became a rival. He's one of the great pioneers in computing. We're interested in the law because it's a way of sharpening perspective. We need a sample problem to work through. Let's suppose we have 4 million floating point values, and we need to compute their average. We're going to do this in two ways. We're going to do it on a single processor machine M1, and then we're going to port the solution to a 4-processor machine M4. We're going to call the problem P, and we're going to make a slightly unrealistic assumption. We're going to assume that M1 and M4 differ only in the number of processors. Everything else is the same. The amount of memory, the amount of cache, all of that stuff. Now, let's jump into the example. So basically what we do is this. We compute the response time for P on M1, so we'll call that response time 1. Do the same on M4, we'll call that response time M4. And then we just compute the ratio. Response time 1 over response time 4. There's basically 3 possibilities. If the ratio is 1, then there's no change. So it wasn't worth the effort to port the solution over to the 4-processor machine. The middle case is actually a disaster. If the ratio is less than 1, that means that RT1 is less than RT4. In other words, we've slowed things down. Our job is in jeopardy. And finally, this is really the expected case. If the ratio is greater than 1, that means RT1 is greater than RT4. Maybe RT1 takes 8 time units and RT4 takes 4 time units. So we wind up with a speed up of 2 because the second machine has 4 processors. Now we want to simplify things a bit, so we're going to normalize the response time 1 to 1. In other words, let's say it took 27 milliseconds to solve the problem on machine 1. We're going to call 27 milliseconds 1 time unit and just be done with it. So it's a simplifying assumption. Step 5 is the absolutely critical one. We're going to take RT4 and break it up into 2 parts, which I'm going to call enhanced and unenhanced. These are traditional terms used in this context. So let me give you the basic idea by getting concrete. We've got 4 million floating point values that we need to process. We need to read them from someplace. Presumably they're on disk. We're going to go parallel, which means we're going to have threads or processes as workers. We need to partition the data set into 4 parts, assign those parts to the workers. The workers are going to do their thing. When they're done, we need to aggregate the results. The partitioning, the reading of the data, and all of that stuff is going to be done in serial. Some of the computation is going to be the same on M4 as it is on M1. there's going to be no speed up. That's the unenhanced part. The enhanced part is the part that's going to be sped up because the parallel computation kicks in. Here in roughly the middle of the document, you see the amended version of this. So speed up is the ratio, and the ratio is now 1 over unenhanced plus enhanced. Now, here's how we compute unenhanced and enhanced. We need to know two things. First of all, what fraction of the computation is in enhanced mode? For this particular example, I'm going to assume 80%. So 80% of the time, we're in parallel mode crunching the numbers. 20% of the time, we're doing the setup and the cleanup at the end. I'm also going to assume that when we're in parallel mode, we're 4 times as fast. That's not an unreasonable assumption because we have 4 times the number of processors. Given all of these assumptions, we now come down to this revised formula. We can now plug in some numbers. So we have speed up equals, and you can see at the end, 1. That's response time 1. In the denominator, 0.2, of course, is the unenhanced, 20%, plus 0.8 is the 80% enhanced, and the 80% enhanced is 4 times faster. So if you do the math in a calculator, it turns out that the speed up is 2.5. Now here's the big picture, and I'm going to use the table at the bottom to summarize this. When looking at speed up, it's sometimes tempting to look at how much faster the local speed up is. So in this case, going from M1 to M4, the local speed up we're assuming is 4, because we have 4 processors on M4. The global speed up, however, depends not only on that local improvement, but on the fraction of time that we use that local improvement. And in this case, we're assuming it's 80% of the time, which is a pretty high number, and we get a global speed up of 2.5. To drive this point home, I've made up a little table. M4, M8, M12, 4, 8, 12, and so forth describe the number of processors on the machine. The next column over describes the fraction of time spent in local speedup, 0.8. And notice I'm assuming that the numbers diminish because I'm assuming that more of the time has to be spent in setup and cleanup at the end. I give the local speedup 4, 8, 12, that's just the number of processors, and then I compute the global speedup at the end. And notice the trend. For a 4-processor machine, under the assumptions given, the speedup is 2.5. When we move to 8, the speedup goes up a bit to 2.6, but then it starts to drop, 2.2, 1.9, 1.6, 1.4, and that's because more and more time is spent, in this example, in serial mode. In summary, Amdahl's law gives us a way to get a quantitative answer to the question, how much faster, if we do this, that, or the other. But just as important, it helps us think about the 2 contributing factors to that improvement. The first is, how much faster is the local improvement, going from 1 processor to 4? What fraction of time is going to be spent in this enhanced mode? This lesson recommends an exercise that focuses on how parallelism can impact performance. Not much coding is required for the exercise. It's really more data gathering and then reflecting on the data gathered. And it involves a program that we've seen already. It's the ParallelSort in Java. So let me remind you of how that worked. There's an array to sort. It holds int values. And there's an array size set to about 4 million. So the program fills the array with values and so forth. It does that in parallel down here at line 4. And then sort array is where the timings are done. 2 sorts are done. One is done in parallel, and the other is done the old-fashioned way, using the original Java sort, the quick sort, and then the timings are compared. So if we jump to the bash shell, I've done some runs already. Let me clear the screen and do another one right here. So I'm running the ParallelSort, and you see the information. The speedup is almost 2.5. Do it one more time for good measure. A little better, almost 3.0. And that's the range that I've been getting, from about 2.4 to 2.8. Now let me go back to the Emacs. So the exercise basically is to gather more data. So the array that I used in this example has 4 million elements. What I'm recommending is something a bit different. Start out maybe with 1,000 or so elements, and then build up an array, which I've done here, 16 values for different sizes. And what I do inside this loop each time, of course, is double the previous size. So the first size is going to be 1024, the second is going to be 2048, 4096, and so forth. The only thing you have to watch is you can't go over 20, so I've set it to 16 because you're going to get integer overflow. If you're going to go over 20, you'd need to use a long instead of an int. The idea then is to run the serial versus parallel for those different array sizes to see if you can spot some sort of trend. Undoubtedly, there's going to be a trend, but it may not be obvious. So for example, on relatively small array sizes, there may not be much difference in performance. As you get bigger, you would assume there's going to be a difference, but you also may peak. You may get to a certain size, after which performance tends to degrade. So the first suggestion then is to try different array sizes with ints, but then also to expand the exercise to consider other data types. So for example, bigger integer types, long, float, and double. In this lesson, we're going to make a transition. In recent examples, the focus has been on SIMD parallelism, and we've looked at this at various levels. We've looked at the assembly language code that the GNU compiler can generate practically on its own. We've looked at the streaming SIMD extensions that are available with Intel machines. And we've looked at a framework, OpenMP, that takes a thread-based approach to auto-vectorization. We're now going to look at parallelism in the context of distributed systems. Let me review very quickly the definition. So a distributed software system is simply one whose pieces execute on physically distinct devices. Common examples are the web and email. Basically, social networking sites are all distributed systems. Almost any application that runs on a handheld device is a distributed system. You can make the case nowadays that the default is the distributed software system. It's really exceptional to find software systems that are meant to run on an isolated computer. That is, a computer that does not rely on the network at all. Now, distributed systems pose all sorts of challenges. We have a networking infrastructure. If that goes down, we're in big trouble. We have a heterogeneous environment. We may be dealing with physical devices that are radically different, run different operating systems, support different libraries, and so on. One of the major challenges, and one that we're going to focus on, is going to be how can the modules in a distributed system communicate with one another in order to solve a shared problem. It's hard to give a nice catchphrase for distributed parallel systems. Some people have suggested MIMD. I'd like to keep this approach as practical as possible, and I'd like to keep the focus on communication APIs. Let's take a very simple distributed system. Let's assume that there are only two devices. We're going to call these host 1 and host 2. The distributed system is just DS, and it has two modules that are of interest to us. Here's a very simple depiction. One module, M1, is hosted on one machine, and another module, M2, is hosted on a different physical device, and they communicate by sending messages. This is a very common approach to communication in distributed systems because by default, we don't have shared memory. We need some other way to go about communicating. Now, there are various standards, various approaches to message passing. But one that's of interest to us is called MPI for Message Passing Interface. I've provided the URL down there. And this is an open source community project. It has industrial strength standards for message passing. And there is an implementation called OpenMPI, and I've provided the URL there. Unfortunately, it is very easy to confuse OpenMPI with OpenMP. OpenMPI has bindings for different languages, for C and C++, but it also has, for example, bindings for Java. They're not quite complete, but they're close enough. OpenMPI has been widely accepted, it's in wide use, it's high level, and it provides support for what people sometimes describe as HPC, high performance computing in a distributed environment. In summary then, our transition is from SIMD parallelism to the kind of parallelism that is now commonplace across network-based systems, that is, distributed systems. So we're going to emphasize the kind of parallelism that is possible if you treat the network as the computer. And our focus is going to be on communication among the modules that make up the system. So we don't care what the system is, we care about the communication among the pieces of the system. We're going to take a look at the MapReduce programming model, which has become, in a very short time, almost a mainstay in distributed systems. Part of the reason for the popularity of this programming model is that the Apache Hadoop project and the associated open source software have become very, very popular. Let me do a little bit of background. First of all, a quick word about the name. It actually comes from Lisp. Let me give you the example. This is actually in pseudo Lisp. I've cleaned up the syntax a little bit, but Lisp has constructs such as the following. There's a map function. You can give this function as its first argument an operator, so in this case plus, and the plus is then applied to members of a list, in other words, to an aggregate. So you might say plus is mapped across this aggregate, and the result is 10. What map does here is adds the numbers in the list, reduces that list to a single value, in this case, the value 10. Now, as noted, MapReduce is not a perfect name for this. The Google engineers who developed MapReduce were inspired by the Lisp example, but a better name might be scatter-gather, because what MapReduce does, in effect, is scatters pieces of a problem across different hosts or processors on the same host in a very simple case, lets those hosts solve pieces of the problem, and then aggregates the partial solutions to get a complete solution. Scatter-gather also describes what's going on behind the scenes. What I'd like to do now is introduce a problem. I want to take something that's reasonably intuitive and commonsensical, but lends itself to a nice, clean implementation. So the example goes as follows. We're going to consider a 200-page book, and we're going to have 4 human editors working together to compile an index. So what they do is they divide the book into 4 50-page segments. So those are the pieces that are going to be scattered across the editors, 4 in this case. Then what each editor does is compile the index for those 50 pages. We're just going to pick one, for example, concurrent, and the result is going to look something like this. We have editor 1, editor 2, editor 3, editor 4. So in MapReduce, you have keys and values, and I'm going to follow that structure. So the key in this case is the term concurrent, and then the value is a list. In this case, the list of pages on which that term occurs at least once. I've made up some pages, as you can see in the example, for the 4 editors. So these scattered partial index now need to be aggregated into a single index. In this particular example, the key remains the same. That's not uncommon. But the result is now the aggregated list. We've taken all of those partial lists of pages, we've put them together in order, and what I've shown up here, of course, is the editor number of the associated editor who compiled the partial list, And the completed list is down here. It goes from 4 all the way through 199. Now, I've shown the aggregation in one step, but of course, there might be partial steps. We might aggregate, for example, the results of editor 1 and editor 3, aggregate those with the results from editor 4, aggregate those with the results from editor 2, and so forth. So there's various intermediate steps that might be taken. The point of interest is we want to get from this scenario, the 4 editors with their partial indexes, down to this final result, one key and the associated value. This lesson sets the stage for doing a MapReduce example in Java, in particular in Java 8. You're looking at the source file streams.java in my Emacs editor. I'm on a Mac, and I should caution that you may have trouble compiling this code on a Mac. I've got some information at the top about this, and in fact, I had to compile on another system and then upload the .class file to execute it here. The packages of interest in Java 8 are java.util.stream. You see that in these two imports, and I'll get into the details in just a moment. So let's jump down to the code. By the way, Java 8 uses the new functional programming constructs, the lambda expressions, and so forth, and you're going to see that in these code examples because they work very nicely with the MapReduce programming model. So to begin, we need a collection, and I create a list of integers. I'm using what is now a standard approach syntactically. I have my list. I'm going to invoke .stream on it, .map on the stream, and then .for each on the result of the mapping operation. So let me back up and just talk very quickly about streams. A stream is an iteration construct, and a stream can be attached to any collection. The important thing is this. Once a stream is used, it's used up. If you look at example 1, I generate a stream, do some things. In example 2, I use the same list, but I have to regenerate a stream. That initial stream, you might say, has been used up in the course of iteration. Streams are efficient. They basically yield elements of a collection on demand. This is sometimes described as lazy evaluation. We're not going to get too much into those details. Our main interest is still in MapReduce. So let me walk through these first two examples, and then I'll show you the output for them. We have the list of integers. We streamify it if you like. So now I can pick up the elements one at a time. The map function in this case, this is the lambda expression syntax, takes each member, I just call it n, and as the arrow indicates, it maps that to the successor, n plus 1. So the integers in the list are 0 through 15, but the output is going to be 1 through 16. Let me jump to the command line. I've saved the output in a file called out for convenience. And you see at the top of the screen the first outputs, 1 through 16. And those, again, are the successors of the values in the list. So back to the Emacs editor. Let's look at example 2. Slightly richer. We still get a stream. Now I'm going to take each element n and map it to a list. And the list is going to be the predecessor of n, and its successor. Then I'm going to, once again, print each one out for convenience. And now you see roughly in the middle of the screen the outputs there. So the first output is -1, 0, 1, then 0, 1, 2, and so on until we get 14, 15, 16. Back to the Emacs editor. What I want to do in the next two examples is to contrast a regular old serial stream with a parallel stream. So example 3 has a regular stream, and 4 has a parallel stream. What I'm going to do in the printout is print the identifier of the thread that's doing the work. Example 4, by using a parallel stream, is going to scatter the work to the threads in a thread pool. Let me jump back to the command line and show you those outputs. In roughly the middle of the screen, 1 through 16, it's the main thread doing all of the work. There's only one thread. Basically, we have a serial stream. In the second example, it's a bit more interesting. 11, 12, and 10 are being managed by the main thread, but then you see 6, 14, 3, and 4 by threads from a fork join thread pool. So under the hood, the parallel stream uses some of the same constructs that we saw much earlier in the fork join framework. And continuing along, you get the total printout for the workers in the fork join pool. I didn't have to set the size of this. I have 8 processors on this Mac, and what the system gave me was a pool of 7 threads, one less than the number of processors. Back to the Emacs editor. There are some implementation issues with parallel streams in Java 8. There's been some fairly harsh criticism. We're interested right now in the API, and Java has a pretty good record of improving implementations of good APIs. Example 5 is going to do not only the mapping, but also the reducing. And this is the most complicated example. I'm going to use a stream iteration, but I'm going to save the result in something I call int sum. I have a parallel stream. If you're going to do reduce, you need a parallel stream. Reduce on a serial stream doesn't make sense. Once again, I'm going to map each element in that stream to its successor, and now I'm going to use the 3-argument version of reduce. So reduce is overloaded. There are different versions. The 3-argument is the richest version, so let me explain the arguments. The first argument is called the identity value. It's the initial value for the reduction. It's also the default value in case the stream has nothing else to deliver up. So if we need an operation from the stream, but the stream has run dry, we get the identity value 0. The second argument is the accumulator. I think this is fairly intuitive. We have a running sum. We have an n that basically maps to a new sum, which is the old sum plus n. The third argument is the combiner function. We have 2 sums, and those map to the sum of the 2 sums. Back to the bash shell. Running this example, we get pretty much what you'd expect. 136 is the sum. And then down below, I've got a trace of the accumulate and the combines. Let me come back now to the Emacs editor. There's example 6, just like 5. The only difference now is that I do some printouts so that we can follow what's going on. The purpose of this lesson is to get a first look at the programming style that we're going to use, and also a first look at the map and reduce functions. This lesson returns to the book index example. We're using this to illustrate MapReduce. We're looking at a code implementation. So in my Emacs editor, you're looking at the file index.java. There are instructions for compiling and running it, and the documentation at the top. There should be no issues even on a Mac, because we don't use the function reduce. We use something similar to that, and it compiles without incident. Once again, we're going to use the java.util.stream package, and we're going to use the so-called functional programming extensions that come with Java 8. And they work well in the current example. So let's look at the main class. It's a POJO class called index, a single field. An index is a map of string keywords that would occur in the index. And the value for each of those is a list of pages. So in this case, it's a list of integers. In the constructor, we set that field to a concurrent hash map. We have to assume that we're in a concurrency environment, and in order to ensure thread safety, we go with this data structure, concurrent hash map. It's efficient, and it's got the thread safety baked in. The index class has 2 methods. Add entry and get entry. So get entry down below is pretty simple. You feed it a word, it returns the list of pages, or null if the word doesn't occur. Add entry is slightly trickier. 2 cases to consider. The index might already contain that word, So in effect, what we're doing is updating the list of pages. That's the if clause logic. Otherwise, this is a new entry, and this is the else clause logic. In any case, that logic is not of particular interest to us. We want to focus on the map reduce aspects. The list is sorted. These lambda expression extensions serve us well. So the sort in this case, there are two parameters, n1 and n2. These are integers. The compiler can figure that out from the context, and basically what we do is compare n1 to n2. This gives us an ascending sort. If this were n2 dot compared to n1, in other words, the second argument first, then we would get a sort in descending order. Once the list of pages is sorted, it's put into the index. Now, index main encapsulates main. Let me go to the initialization section of the code. This is the private init method. It creates a list of lists. So I've named the object reference LOL. Each of those integer lists is going to be compiled by a single editor. And what we're going to do here is put all of those editor contributions together. I've mixed up the order for the editors, and I've added some editors. In the original example, I had 4. Now we have 8. And I'm just making up pages. So if you focus on the first entry here for editor 4, here's what we can assume. The editor puts the pages in ascending order: 162, 176, 187, 199. But the editor represents a separate processor. So this is a distributed system environment. We have no idea what order we're going to get the results from the editors, so I've deliberately mixed up the order. First we get the result from editor 4, then from 3, then from 8, and so on. We're going to have to sort the list eventually, because even though the nested lists are in order, the overall list is not. There's a second utility function, and this is where the MapReduce functionality of Java 8 comes to the surface. This is called flatten. What we need to do is flatten a list. So in the documentation, here's a very quick example. The list of lists conceptually looks like this. We have an outer list, then we have some inner lists. The first inner list is 1, 2, 3. The second is 9, 8, 7, 6, and so forth. We want to flatten the list by basically extracting the members from the nested lists and wind up with a single list with the page numbers in it. And that's what the flatten method does. To create a flat list, which is a list of integers, we take the LOL parameter, the list of lists. We generate a parallel stream. So we're going to have multiple worker threads do the work. Each of those threads basically is going to take one of those nested lists. And what it's going to do is flat map it. In other words, the N is going to be a nested list, for example, list 1, 2, 3, and it's going to generate a stream of integer values out of that. So in this case, 1, 2, and 3. The very nice collect method is going to collect those individual values, 1, 2, 3, 9, 8, 7, 6, and so forth, and basically put those in a list, and that list in the end is going to be what I'm calling the flat list. So flatten takes a list of lists, flattens it to a single list of page numbers in this case, and returns it. Here we come down to the function that actually is called from main and does the work. The first thing we do is call init. That gives us all of the results from the editors. We flatten that list, create an index, add an entry. To confirm that this worked, we get the entry. And then for good measure, I'm going to pretend that there's yet another editor. This, after all, is a distributed system. We never know when these inputs are going to arrive. We get the compilation from yet another editor, editor 9, and we add that to the already existing entry, and that should show up then in the index map. And as we'll see, it does. So let me now run the program. I've compiled it already. I'm back on my Mac. The first output is for Concurrent, and you see that the page numbers are all in sorted order, and we've got a flat list. 4 is the first value, 399 is the last. And then the second output reflects the additions from Editor 9, who added 401, 402, 417, and 435 at the end. In summary then, because of the popularity of MapReduce, you see deliberate explicit support for the MapReduce programming model in the APIs that now come with java.util.stream. In this lesson, we're going to take our first close look at MPI and OpenMPI. MPI stands for Message Passing Interface, and OpenMPI is an implementation. OpenMPI sounds a lot like OpenMP. Recall that OpenMP is a framework for doing SIMD, or data parallel programming, through multithreading. MPI is the specification for passing messages among the component processes of a parallel software system. Now, this system also might be distributed. Looked at this way, MPI is really an inter-process communication mechanism of the sort that we saw when we did multiprocessing. Now let me introduce some other acronyms. MPI supports what people call SPMD, Single Program Multiple Data Programming, and this is arguably the most popular style of parallel programming. You can look at SPMD as a subtype of Flynn's MIMD, Multiple Instruction, Multiple Data. And the idea is you have a single program, and each program is going to generate multiple processes, and those processes can divide up the labor in whatever way is appropriate. In dividing up the labor, those processes probably are going to be working on different data streams. SPMD is said to support HPC, high performance computing, through parallelism. There are two well-known implementations of MPI, OpenMPI, you see the URL, and there's a second one called MPitch, and I've got the URL there as well. We're going to use OpenMPI. It's available on all of the standard platforms. In an OpenMPI program, you've got multiple processes. These can use the multiple processors on a given host machine, or the processors distributed among the devices in a cluster. What it needs to do is have processors to execute the processes. If you're going to run OpenMPI in a distributed environment, in other words, in a cluster of devices, there's some system administration work to be done to define the nodes that make up the cluster and that sort of thing. Now let me get a little bit practical, because we're going to see a couple of OpenMPI examples. I want to walk through compilation and running, and then talk about the standard structure of a program. First, to compile, we've installed OpenMPI on whatever platform we happen to be using. As part of the install, we get the MPICC utility. That's the compiler. So I use that to compile my source code, and then I generate whatever output file I want. And then when I go to execute, I use MPI run. There are various flags available, but the most common one is the -MP for number of processes. I'm going to set that to 8 in this case. And then I feed MPI run the name of the executable. Within the program, there's a standard pattern, and I've numbered the steps 1 through 4. We initialize OpenMPI. We get the number of processes involved. OpenMPI calls this the size, and the size is typically passed in as a command line argument. In the example above, -MP8. So the size for this program would be 8. Each process has an ID. In OpenMPI, it's called a rank, and it's basically 0 through size -1. So if we have 8 processes, those have ranks of 0, 1, 2, all the way through 7. This is for ease of identification of a particular process. We can send and receive messages among the processes as needed. So for example, process 1 could designate a particular message for process 7. Process 7 could say, I'm interested in receiving a message from process 3 or from any process whatsoever. So as we're going to see, there's some flexibility in the API. And then in the end, we close down MPI gracefully. In this lesson, we're going to look at our first code example in OpenMPI. Recall that OpenMPI has different language bindings. So for example, there is a binding for the C language, for C++, for Fortran, for Java, and for other languages as well. The Java binding is not complete, although it's still pretty solid. We're looking at an example of the C binding. In my Emacs editor, you're looking at the source file mpibasics.c. Here for review is how you would compile this using the mpicc utility. And this is how you would run it. The flag -mp stands for the number of processes we want. So we're going to do multiprocessing, and OpenMPI is going to handle the details for us. In this particular example, there's no inter-process communication, no sending or receiving of messages. We'll pick that up in the next lesson. Let's get to the source code. So the third include is for mpi.h. This comes with the installation. It's the standard header file. To keep things simple, I've got a single function called main. When this is run, all 4 processes, assuming that's what we ask for, are going to execute exactly the same code, the body of main. Recall, when a parent forks a child process, the parent and the child then proceed to execute the same code, and so programmers use if-else constructs or the equivalent to divide what the parent should do from what the child should do. You're going to see a very similar pattern here. But there's automatic multiprocessing that OpenMPI does for us. So to begin, 2 local variables, rank and size. Size, again, is the number of processes. So if we ask for 4, we're going to get 4. And rank is going to be the ID of each process, 0 through 3. I set these to -1 because those are illegal values and we should pick something else up momentarily. This is the MPI initialization. Traditionally, the 2 arguments are argc and argv, which can be passed into main. I'm not bothering with that because OpenMPI doesn't do anything with those arguments. So I've simply set those to 0 and 0, which, if you're not a C programmer, are basically null pointers. So we don't need the arguments to be anything more than 0, 0, but we do need to call the init to get the environment set up. This call to size gets the number of processes. The second call to rank gets us the ID of each process, because again, all 4 processes are going to execute this code. All 4 get their own copies of these local variables. In both of these function calls, the MPI COM_world, that first argument represents, in effect, the communicator, which is the context for sending and receiving messages. Let's now get down to the division of labor. If rank is 0, that's the so-called master process. We first check to make sure we have enough processes for this program to be done well. Otherwise, we print a little reminder of how to call it. The master process then just announces itself and says how many workers it has. It should have at least 3. Then workers 1 and 2 print out simple greetings. Worker with the ID 3 does a bit more work, sums up the integers from 1 through 1,000. After that work is done, finalize is called. This is the graceful cleanup. So the code is straightforward, but it does contain the basics, in particular the if-else structures that are used to divide the labor in a so-called single program multiple data model of parallelism. Let's jump now to the command line, to the bash shell, and run this a few times. You can see that the output comes first from the master. then from worker 2, then from worker 1, then from worker 3. All of these are separate processes. We run it again. We get a slightly different order. We run it yet again. We get a different order. We run it yet again. Still another order. This underscores the unpredictability that comes from a true multiprocessing environment, where we're doing parallel execution of multiple processors. I'm on a Mac that happens to have 8 processors, so those 4 processes can be running literally at the same time. So this first example covers the basics of OpenMPI programming. In the next code example, we'll get into sending and receiving messages. In this lesson, we're going to focus on the core idea in MPI, message passing. The context, of course, is that we're doing parallel computing in an environment that has multiple processes. The work is being divided up among these processes. And since these processes are working on a common task, there needs to be some means for them to communicate. And message passing is the standard inter-process communication mechanism under MPI. So let's look at this now at the code level. The source file you're looking at in my Emacs editor is mpi sendReceive.c. Let's jump down to main. Each of the processes that OpenMPI generate is going to execute this code. So once again, we're going to use an if-else structure to divide the labor. To begin, we've got some buffers for sending and receiving data. I call this digits out and digits in. They're basically character codes, 8-bit bytes, ASCII codes in effect, because this is C. The 2 memset calls simply clean out the buffers, put the so-called null terminator in all of those. The null terminator is a non-printing character in ASCII. Once again, we have the rank and size. We've seen that before. The status is new. On a receive operation, the status is going to contain metadata about the reception. So the MP status is going to be an additional argument in the receive function. Otherwise, the send and the receive are basically identical. Once again, the usual 3-step to set things up. The init we've seen before. We get the size, that's the number of processes. And we get the rank, or the numeric value that identifies each process uniquely, starting at 0. So 0 through size -1. The if-else construct is very useful for dividing the labor. So if the rank is 0, this is the so-called master process. It's going to get things rolling. First, there's a little usage logic. If we don't have at least 2 processes, there's no point in doing much. Then what the master does is the following. It takes its rank, 0, and it basically copies it into the output buffer. So the output buffer consists of a single printing character, 0, and the so-called null terminator. The master then calls send, and the arguments are as follows. The data to be sent, it's an array, a buffer. How many things are to be sent out of that buffer? To keep this general, I'm computing the string length. In this case, it's going to be 1 plus 1 for the null terminator. In an array, of course, all of the elements have the same data type, MPI_char. This is basically a C char. It's an 8-bit character code. The destination is really important. We're going to send this to rank, which is 0 plus 1. In other words, process number 1, which is the first of the workers. So again, to keep this general, I have rank plus 1 in there, although we could just hardwire it to 1. This is user-defined data. It could be anything we like. I'm not using it in this example, so I simply put a 1 in there. And the communicator we're using is the built-in one called MPI_com_world. If we wanted to get fancy, we could build our own communicator. The master may get a message as well, but to begin, I'm going to ignore the receive in the master and focus on the send, because the receive will become clearer when we look at the workers. So let's jump down to the workers. all of the worker processes are handled in a single else clause. They all start out with a receive. So each one does a receive into its input buffer. Max length is in here because the workers don't know how many characters are coming. We take up to max length, which in this case is 64. The data types again are characters. MPI any source is very useful here. Instead of hardwiring the source by giving the rank of a particular process, so for example 0 for the master, we leave this open. This is a very nice feature in the API. Once again, this is the user-defined data. This again is the communicator, and the additional argument is the status. We can look at metadata about the message reception if we like. The first thing a worker does is report what it got, and then the worker creates an output buffer consisting of its input buffer plus its own rank. So you might say what a worker is doing is taking what it got and adding some additional information to it, and the worker then does a send of its own. It takes the output buffer, we compute the length, they're all characters, and it's going to send it to the next in line, to worker 1, to worker 2, to worker 3, to worker 4, and so on, until eventually we go back to the master. The master does a reception of its own, but after that reception, the master is done. There is no more sending. Now, a couple of quick points about the send and the receive. They're both blocking calls. The send blocks until the data reach the destination process, and the receive blocks until the data fill its input buffer. The receive actually could complete before the send does. Suppose the send sends 5,000 bytes, just to pick a number, and suppose the receive is going to receive only 200 bytes. As soon as the 200 bytes are in the input buffer, the receive basically is done, even though the sender is still sending more bytes. Now let me jump to the command line so you get the idea of how it works. So I'm going to start out with 2. The master process and the worker process have outputs. The order again is indeterminate. We're in a multiprocessing environment, so the worker process received 0. The master process received 0 and 1. So the 0 and the 1 are the rank of the master and the rank of the worker. If we increase the numbers, jump up to 4, it becomes more interesting. Let's jump up to 8, and then of course we'll go to 16. Basically what's happening is the workers are receiving messages, creating new messages, sending those messages to the next worker until eventually we wind back to the master. The master receives, reports, and then terminates. So this program covers the basic API for inter-process communication in OpenMP. This lesson is a wrap-up of the recent code examples. Those code examples have focused on 2 things. The first thing has been the map-reduce programming model that illustrates the scatter-gather pattern. We take a problem. In our case, it was the book index problem. We need to compile an index for a book. We break that problem up into subproblems. We scatter the subproblems to individual editors. So editor 1 covers certain pages, editor 2 covers other pages. And then at the end, we have a chief editor who gathers together the partial results and compiles the final index. The scattering could be done in multiple stages. The gathering could be done in multiple stages. The data structure emphasizes key-value pairs. So in the index problem, the particular word, for example, concurrent, is the key, and the value for that key is a sorted list of pages on which the word occurs. So it's a very clean programming model. How it fits into the depiction you see in this document, wrapup12.txt, we'll get to in just a moment. The other code examples focused on the OpenMPI implementation of MPI, Message Passing Interface, and this is an implementation that emphasizes SPMD systems, single program multiple data systems. You have a single program, And that single program does automatic multiprocessing. Each of those processes can handle different data streams. What I'd like to do now is turn from the examples to what we need to carry out those examples. To do parallel computing, we need multiple processors. We also need some means for those processes to communicate, because the assumption is that we're working on a single problem. There's one task, and all of the processes are workers contributing to the task. So communication is essential as well. What we've not focused on is any architectural detail, so I'd like to address that now in the wrap-up. If you look at this very simple depiction, I have two things: a multiprocessor machine at the top that's got 8 processing elements. I've not described how those are arranged on the machine. This could be an 8-core machine. Each core has 1 processor. It could be a quad-core machine. Each core has 2 processors. You could have the case, for example, where the cores have an L1 cache. More modern cores might have both an L1 and an L2 cache. If you have a single processor on a core, that L1 cache is dedicated memory. But on this particular system, main memory is shared among the cores and so among the processors. We didn't get into any of those details because the programming model and the framework that we used shouldn't care. Basically, in this case, it doesn't care. It would work on this single processor machine regardless of whether those processors each were on its own core or you had multiple processors on one core. The second picture depicts a truly distributed environment. We have a cluster of processor nodes. I've shown those down here. The assumption in OpenMPI is that each of those nodes has its own memory, but each of those nodes could be something fairly complicated. It could be a multiprocessor machine. That detail shouldn't matter. In the case of OpenMPI, it doesn't matter. There are other issues that don't matter. For example, it's possible that the processes in our application are in fact multi-threaded. So we might divide the work not only among processes, but then the processes might take that work and divide it further among threads. Under either the MapReduce programming model or the OpenMP framework, these are perfectly fine alternatives. OpenMPI in particular doesn't care how simple or complicated the individual processes are. The thing that OpenMPI focuses on is communication at the process level. Now, as we know, on modern systems, a process is at least a single thread, so the communicator is really a thread of execution. It could be the single thread in a process, it could be one of many threads in a process. So the point is, in the examples that we've seen, there's been very little attention on architecture. The only real assumption we've made in every case is that we ought to have multiple processors. That's the only way you get, of course, truly parallel execution. Otherwise, you have multiple processes sharing a single processor. The fact that we haven't looked at architectural detail is deliberate, and one of the really nice features about both the MapReduce programming model and the OpenMPI implementation of MPI is that they allow us to ignore these architectural differences. Those become system administration issues. This lesson proposes a programming exercise. The idea is to take the MapReduce example that we saw, the book index problem, and give this an OpenMPI implementation. So let me go back to the source code. This was the Java source, index.java, for the MapReduce problem. Let me explain how it was handled there and what the difference would be. So if you look at this method called init, it creates a list of lists, and each of those nested lists represents the work done by one of these individual editors. The key in this example is the word concurrent, and the value is going to be the list of pages on which this occurs. The index.java example picks up the action, you might say, midstream. we've assumed that the editors have done their work. So you see editor 4, editor 3, editor 1. The work is being submitted in no particular order. So that's to give an air of realism to this. They have submitted their partial results, and the job now is for the chief editor to aggregate those results. So the chief editor is going to do the gather phase, and that's done in this function called flatten. So it takes the list of lists, it generates a parallel stream. Each worker now is an individual thread. What each of those threads does is to take a nested list. So in the example up here, 1, 2, 3 is a nested list, 9, 8, 7, 6 is a nested list, to streamify those nested lists so that the chief editor then can collect all of the elements into a single list. So in this case, the single list would start 1, 2, 3, 9, 8, 7, 6, and so on. Later on, there's a little more work the editor needs to do. The editor needs to sort that list so that the page numbers are in ascending order. So the idea in this exercise is you would use OpenMPI to do the init part. You would have separate processes. Each process would represent one of these editors. Each editor would assemble a sublist and then use message passing to get that compiled sublist back to the editor. So the editor, in effect, would be the master process. The editor then would do the final compilation, the final reduction. So message passing would be used in two ways. The first way would be from the chief editor to the other editors to distribute the work. That's the map phase. And then second, each of the individual workers would send a completed partial list back to the editor for final compilation. This is a challenging programming exercise, but it would be a wonderful use of OpenMPI, so I hope you get a chance to take a crack at it. This lesson is the course wrap-up. We've seen all sorts of code examples. We've looked at different programming languages, programming models, frameworks, and so on. One way to make the wrap-up manageable is to focus on the three big themes, the themes that occur in the course title: concurrency, parallelism, and non-blocking I/O. Let's begin then with concurrency. Many modern apps, any app that has a GUI, any app that offers a service that has requesting clients, needs to manage concurrency. Such applications, by their very nature, have concurrent tasks, and the question, of course, is how best to manage those tasks. The classical approaches are multiprocessing and multithreading. A relatively recent approach is non-blocking I/O. And one thing we saw is that most real-world systems use some sort of hybrid approach. They use some combination of multithreading, multiprocessing, and non-blocking I/O. The second theme was parallelism. From the viewpoint of concurrent programming, parallelism is attractive because it's an efficient way to manage concurrent tasks. We take the concurrent tasks, we farm them out to separate processes, single-threaded processes, to multiple threads within a given process, or to a combination thereof. Our first look at parallelism focused on its connection to concurrency, but we then moved to uses of parallelism that go beyond concurrent programming. We looked, for example, at SIMD, or data level parallelism. We saw it at the instruction level, the thread level, the process level. We looked at single program, multiple data programming, the sort of programming that OpenMPI and other frameworks encourage. We looked at the MapReduce programming model. We looked at parallelism in the context of distributed programming, using clusters of nodes instead of just multiple processors on a given machine. Now, the third big theme was non-blocking I/O. Among the machine-level instructions that execute when a program executes, the I/O instructions remain the slow guys on the block. So any application that has to wait for an I/O operation to complete is wasting time. The challenge, of course, in using non-blocking I/O is to figure out what to do with the time that otherwise might have been wasted. And this takes ingenuity, it takes experimentation. Now, we've covered a lot of topics, but we certainly haven't exhausted what could have been covered. In doing parallelism, I talked a little bit about general-purpose GPU programming. In other words, using graphics processor units as special-purpose CPUs. And there's a very nice framework for doing that. It's called CUDA. The only limitation is it works only with NVIDIA devices. OpenCL is another framework. It's really C, C++ oriented, but you can use it to write programs that run across heterogeneous platforms, and OpenCL is quite powerful. It can handle CPUs, GPUs, floating point units, DSPs, and so on. These are perhaps a bit more difficult than the frameworks that we looked at, but they're in the same spirit of trying to take full advantage of the opportunities for parallel programming that all of us now have, because almost all of our devices are multiple processor devices. So the question is where to go from here. I have two fairly straightforward suggestions. One would be to take the code examples that have been provided in the course and to make them better, to expand them, to make them more efficient, to play with them. The best way to become really good at concurrency, parallelism, and non-blocking I/O is to code as much as possible.